Good morning, everyone. My name is Ali Munir, and I will be serving as the designated federal official for the U.S. EPA Science Advisory Committee on Chemicals, which we refer to as SACC. For this meeting and in my role, I will be opening this public meeting, and I want to thank Dr. George Cobb for agreeing to serve as the chair of the committee for this meeting. I also want to thank the members of the committee, ad hoc reviewers, and the public for attending this important meeting. We appreciate the time and effort of the committee members in preparing for this meeting, and also taking into account their busy schedules. Additionally, I want to thank the EPA Office of Pollution Prevention and Toxics, which we refer to as OPPT, and my colleagues at the Peer Review and Ethics Branch in EPA for their hard work in preparing for this important review of EPA's 2024 Draft Risk Evaluation for 1,1-dichloroethane and Draft Human Health Hazard Assessment for 1,2-dichloroethane. By way of background, the SACC is a federal advisory committee that provides independent scientific peer review and advice to EPA on chemical-related issues regarding the impact of the proposed regulatory actions on the human health and the environment. The SACC provides advice and recommendations to EPA. Decision-making and implementation authority remains with the agency. The SACC is comprised of experts in toxicology, environmental risk assessment, exposure assessment, and also related scientists. When needed, the expertise of these members is augmented by ad hoc peer reviewers who are temporary participants in the SACC activities, providing their additional scientific expertise. In order to assist in the reviews conducted by the SACC committee, as the DFO for this meeting, I serve as a liaison between the SACC and the agency. I'm also responsible for ensuring provisions of the Federal Advisory Committee Act, or FACA, make sure that that's met. SACC meetings are subject to all FACA requirements. These include open meetings, timely public notice of public meetings, and also document availability to the public. Copies of all present EPA presentation materials, written public comments, and other documents related to this meeting are available in the public docket at regulations.gov. The docket number and website are noted in the meeting agenda. As the designated federal official for this meeting, a critical responsibility is to work with appropriate agency officials to ensure that all appropriate ethics regulations are satisfied. In that capacity, committee members receive training on provisions of the federal conflict of interest laws and scientific integrity trainings. In addition, each participant has filed a standard government confidential financial disclosure report. Our Deputy Ethics Officer for the Office of Program Support and their team, in consultation with the Office of General Counsel, have reviewed these reports to ensure all ethics requirements are met. The SACC will review challenging scientific issues over the next 4 days. We have a very full agenda and meeting times are approximate. Thus, we may not keep to exact times as noted due to the discussions and public comments. As we move through the proceedings, we will move to the next agenda item if an item takes less than the anticipated time. We strive to ensure adequate time for agency presentations, public comments, and committee deliberations. For presenters, SACC members, and public commenters, please identify yourselves as you speak into your microphones, since this meeting is being webcasted, transcribed, and recorded. Members of the committee and ad hoc reviewers are encouraged to fully consider all written and oral public comments submitted for this meeting. I would like to note that we have a live video webcast of this meeting through YouTube. To access it, please go to the link in the meeting website listed in the agenda. Please note that registration to attend this meeting is open until the last day of the meeting. For members of the press, EPA Media Relations staff are available to answer your questions about this meeting. Please address all questions to press@epa.gov. At the conclusion of this meeting, the SACC will prepare a report as a response to the questions posed by the agency, the background materials, presentations, and public comments. This final report also serves as the meeting minutes. We anticipate the final report and meeting minutes will be completed approximately 60 days after the meeting is concluded. Again, I wish to thank the committee, ad hoc peer reviewers, and the public for your participation. I'm looking forward to both a challenging and interesting discussion today and over the next 3 days. I will now turn the meeting over to our esteemed chair, Dr. George Cobb. Thank you, Dr. George Cobb.
Thank you, Ali. And welcome everyone. I will not offer more thanks because we're going to be short on time this meeting. I will say my name is George Cobb. I am the chair of the Environmental Science Department at Baylor University, and I'm an environmental analytical chemist with exposure assessment experience as well. And at this point, I'd like to move to our committee, where I'll ask each person to identify themselves and give a very brief synopsis. So first up is Dr. Apte.
Hi, my name is Udayan Apte. I'm a professor at the Department of Pharmacology, Toxicology, and Therapeutics at University of Kansas Medical Center. I'm a board-certified toxicologist and expertise in liver toxicology and human health effects.
Thank you. Dr. Baker.
Hi, I'm Marissa Baker. I'm an assistant professor at the University of Washington in Seattle, Washington. My training is in industrial hygiene and exposure assessment.
Thank you. Dr. Ike.
Hi, my name is Stephanie Ike. I'm an assistant professor at Emory University in the Department of Environmental Health, and I'm an environmental epidemiologist studying primarily persistent chemical exposures.
Excellent. Thank you. Dr. Fong.
Hi, good morning. My name's Art Fong, and I am the technical leader for Smarter Chemistry at Apple. Smarter Chemistry is where we're using or pioneering the use of chemistry innovations to design our products to make sure that they are safe for our workers, our customers, our recyclers, and better for the environment. Thank you.
Thank you. Dr. Fox.
Hi, good morning. Mary Fox here. I'm an associate practice professor in the Department of Health Policy and Management at the Johns Hopkins Bloomberg School of Public Health. I'm a human health risk assessor with training in environmental and occupational health policy.
Thank you. Dr. Graham.
Morning. I am Cynthia Graham. I am an independent toxicology consultant, and my expertise is basically respiratory and normal sensitization.
Thank you. Dr. Jenkins.
Good morning. I'm Allison Jenkins. I'm a regulatory toxicologist at the Texas Commission on Environmental Quality in Austin. Thank you.
Dr. Lee.
Hello, my name is Li Li. So I'm assistant professor at University of Nevada, Reno. I was trained in environmental chemistry and exposure science. My research focuses on developing and using computational models to simulate how chemical substances change, transport, build up in the environment, and how they get into the human body and cause different health problems. Thanks.
Thank you. Dr. Merced Nieves.
Good morning. My name is Francesca Merced Nieves. I'm an assistant professor at Icahn School of Medicine at Mount Sinai in the departments of Public Health and Environmental Medicine and Climate Science. I'm a neuroscientist with experience in neurotoxicology and children's environmental health. Thank you.
Dr. Rumpler.
Good morning. My name is Mark Rumpler. I'm a clinical chemist and toxicologist and laboratory director for Thermo Fisher Scientific.
Dr. Samuel.
Good morning. I'm Jennifer Sommel. I am an exposure scientist and human health risk assessor, as well as an industrial hygienist, and I'm with Insight Exposure and Risk Sciences.
Excellent. Thank you. Mr. Wright. I see Mike's picture there.
Okay, sorry. my computer was not unmuting my audio. My name is Mike Wright. I served as the Director of Health, Safety, and Environment for the Steelworkers Union. And my training is in industrial hygiene. My expertise with regard to this committee is in occupational exposure assessment.
Excellent. Thank you. So that seems to be everyone on the list. Did I miss anyone who has joined us from the committee? I see Dr. Hernandez.
Yeah. Good morning. I'm Jose. I am part of the System Assessment Center at the Argonne National Lab. I am working in computational LCA. I have expertise in environmental modeling, computing for environmental simulations.
Thank you. Is there anyone else that we missed?
Yes, Sabina. This is Sabina Stice, Senior Toxicologist, United States Food and Drug Administration.
Thank you, Dr. Stice.
Yes,
And
and this is Dr. Robin Ann Gentry. I am a principal and board certified toxicologist with Ramble Consulting with over 35 years experience in human health risk assessment.
You know what? I'm just realizing, excuse me, folks, I just went through the first page. There's 2 pages here, and this is totally my fault. I apologize. That was just the committee members. I just saw what happened there. But Robin Ann, I did forget you. So let's continue on, and my apologies. Dr. Engel, is Dr. Engel with us?
Yes, good morning. Bernie Engel, Purdue University, Environmental Fate and Transport Modeling, Professor in Ag and Biological Engineering.
Thank you. And Dr. Kaluzny.
Good morning. I'm Yulia Kaluzny. I am European Registered Toxicologist. I'm biochemist and cell and molecular biologist with expertise in non-animal approaches for hazard and risk assessment.
Thank you. And Dr. Landis.
Hi, I'm Wayne Landis. I'm a research professor emeritus at Western Washington University. I do environmental risk or ecological risk assessment and toxicology.
Thank you, Wayne.
Sure.
Dr. Malberti.
Hello, I'm Silvia Malberti, and I'm an exposure scientist, industrial hygienist, and risk assessor for ExxonMobil Biomedical Sciences. My expertise for this committee is going to be more on the occupational health perspective.
I just realized I missed Heather Lynch.
Thank you. Yeah, Heather Lynch. I'm with Integral Consulting. I'm a board certified toxicologist, health risk assessor with expertise in occupational and consumer exposure as well. Thanks.
Thank you. Dr. Rose.
Hello, good morning. I'm Jane Rose. I'm a toxicologist at Procter & Gamble within the Global Product Stewardship Organization, and I have expertise in read across and inhalation tox. Thanks.
Okay, now I think I got through everybody. Is there anyone now that I missed? I think Dr. Sue is sleeping after a long flight. Okay, with that, it's time for us to move into the remainder of our meeting. And the next person up today is Dr. Reeves, the Director for the Office of Pollution Prevention and Toxics, who's going to give us a welcome and some introductory remarks. Welcome, Dr. Reeves, and we look forward to hearing from you.
Great. Thank you, Dr. Cobb. Can everybody hear me?
Yes.
Great. Thanks for that confirmation. My name is Dr. Alyssa Reeves. I'm the Director of the Office of Pollution Prevention and Toxics here within EPA's Office of Chemical Safety and Pollution Prevention. I'd like to kick things off by thanking members of our committee today for giving your time and expertise to this important effort, and to the 1,1-dichloroethane and 1,2-dichloroethane team for their hard work. I would also like to thank members of the public who have provided written comments and who are presenting oral comments today. I would also like to thank Ali Munir, the designated federal official, and the staff in the peer review and ethics branch for organizing this meeting. It takes all of us in order to get this accomplished. And I also know there's a lot of material to evaluate for this peer review. Thank you for the work that you've done up to this point to prepare. I know it's a lot. And for the additional work that you'll do even after the meeting to develop the report. We are looking forward to your input and advice that you will provide this week. TSCA requires that we use the best available science in our assessments, and I believe transparency and collaboration are key to achieving these goals. Peer review is an incredibly important part of our risk evaluation process. Your feedback helps us determine if we're on the right track, if we need to shift course, and if we need to consider things that we haven't thought of before. Ultimately, your feedback makes our risk evaluation stronger and more robust. Consistent with EPA's scientific integrity policy, we have provided a set of targeted charge questions about science issues related to interpretation of various studies and how best to use those studies to inform the risk assessment or risk evaluations for 1,1 and 1,2 dichloroethane. We recognize that we added these 2 charge questions late in the process. However, these new questions were added in response to public comments that were made at the August 27th preparatory virtual meeting on the scope and clarity of the draft charge questions. We do appreciate your flexibility and are looking forward to getting your input to help us make improvements to our systematic review approach, as we are focused on continuous improvement here in OPPT, and this is part of that consideration of ways for us to always improve our processes. So with that, I know there's a full agenda today, and you'll be hearing a series of presentations from my team on the 1,1 and 1,2 dichloroethane. So I'll close here. Thank you again, and we're looking forward to a productive meeting this week. Dr. Cobb?
Thank you. And thank you for that information. And we do look forward to working with your staff to go through these questions and provide useful feedback to you. And that is definitely our goal. So now we're going to move into the presentations by the agency. And I believe it looks like the first presentation is by Dr. Chappell.
Good morning, everybody. Thank you, Dr. Cobb, and thank you, Dr. Reeves. My name is Seema Chappell, and I'm from the EPA's Office of Chemical Safety and Pollution Prevention. And actually, I will have you advance to the next slide, please. So I want to start off by thanking the members of the SACC for their participation and the feedback that we'll receive throughout our meeting. I also want to thank the public commenters that we will be hearing from as well. Today, we'll focus on the draft risk evaluation for 1,1 dichloroethane and the draft human health hazard technical support document for 1,2 dichloroethane. Next slide, please. So first, I want to say thank you. It takes a small army of talented scientists and experts to get us to this point, including the authors and contributors to the risk evaluation and the technical support staff. I also want to thank our contractors who make much of this work possible, as well as the technical experts from within other EPA offices. Next slide, please. So as an overview, the outline for the presentations during the meeting are shown here on this slide. The technical presentations are aligned with the charge questions that have been posed by EPA, and those are shown on the rightmost column. So to begin, I'll provide a brief introduction to TSCA. Next, Janet Burris, EPA's 1,1 dichloroethane assessment lead, will address background on 1,1 dichloroethane and 1,2 dichloroethane. Neria Arentis, the general population exposure lead, will discuss environmental exposures associated with 1,1 dichloroethane. Jennifer Brennan, environmental exposure assessment lead, will address the environmental hazard read-across approach. Janet Burris and William Irwin will cover the human health hazard read-across approach. Kathy Anatole and Ali Shahodi are human health assessors, as well as William Irwin, will discuss the non-cancer and cancer human health hazard assessment for 1,1-dichloroethane and 1,2-dichloroethane. William Irwin and Greg Masick, our 1,1-dichloroethane occupational exposure lead, will address assessment of dermal absorption and related data, as well as the occupational exposure considerations for 1,1-dichloroethane. Next slide, please. So let's get started with the TSCA regulatory context. TSCA's Section 6B requires EPA to conduct risk evaluations to determine whether a chemical substance presents an unreasonable risk of injury to human health or the environment. So in order to do that, we're asked to not consider the cost or other non-risk factors, including an unreasonable risk determination to potentially exposed or susceptible subpopulations identified by EPA as relevant to the risk evaluation under the conditions of use. Next slide, please. So under the law, EPA is asked to evaluate the existing chemicals with clear and enforceable deadlines. In this case, we have 3 to 3.5 years to complete risk evaluations after the final scoping documents are published. So we must use the best available science, using reasonably available information, and make decisions based on the weight of scientific evidence. We'll talk more about all this later. Our goal is to develop a risk-based chemical assessment without consideration of cost or other non-risk factors, and we must consider risks to potentially exposed or susceptible subpopulations determined to be relevant to the risk evaluation. Finally, we need to address those unreasonable risks identified in the risk evaluation. Next slide, please. The risk evaluation considers the exposure and hazards to determine whether a chemical substance presents an unreasonable risk to human health or the environment under the conditions. The risk evaluation is our primary science support document that the agency uses if it is necessary to issue regulations to address an unreasonable risk. Finally, to the extent that the administrator makes a decision based on science, the administrator shall use scientific information, technical procedures, measures, methods, protocols, methodologies, or models employed in a manner consistent with the best available science, as addressed in Section 26H of TSCA. Next slide, please. So let's make sure to address some key scientific terms so that they're properly understood here as we go through the evaluation of our work. Specifically, EPA will document that the risk evaluation is consistent with the best available science and based on the weight of scientific evidence. In determining the best available science, EPA needs to consider the extent to which scientific information, technical procedures, measures, methods, protocols, methodologies, or models that are employed to generate our information are reasonable and consistent with the intended use of the information. So some of the charge questions that you'll see also require consideration to the extent to which the information is relevant for the administrator's use in making decisions about the chemical substance or mixtures. We also need to consider the degree of clarity and completeness with which the data assumptions, methods, quality assurance, and analyses employed to generate the information are documented. The extent to which the variability and uncertainty of the information or in the procedures and measures, methods, protocols, and methodologies or models are evaluated and characterized. So that's why we're so focused on methodologies in our charge questions. Then finally, the extent of the independent verification or peer review of the information, which is the reason why we're asking for this guidance today. Next slide, please. In order to meet the requirements under the law, TSCA risk evaluations must be made on the weight of scientific evidence. EPA relies on established agency guidance documents, which provide consistency and formality to the process. These help integrate multiple and often heterogeneous lines of evidence. The weight of scientific evidence assessment is based on the strengths, limitations, and interpretation of the data available across multiple lines of evidence, and how these different lines of evidence may or may not fit together when drawing conclusions. The weight of scientific evidence assessment also examines multiple lines of evidence from scientifically relevant published or publicly available studies in peer-reviewed scientific journals. Studies conducted in accordance with OECD or EPA guidelines, gray literature, and other studies, scientific information, or lines of evidence that are of sufficient quality, relevance, and reliability. These are evaluated across studies and endpoints into an overall assessment. EPA has provided a summary of the weight of scientific evidence narrative to accompany a detailed analysis to transparently describe the conclusions as well as explain the selection of studies or effects used in the main lines of evidence, which serve as the relevant basis for those conclusions. Next slide, please. So when we start, there are a number of considerations. We look at sources of potential exposure, the pathways by which those exposures may occur, the media in which those exposures could take place, the people and organisms that may be exposed, and then the routes by which people and organisms may be exposed. Next slide, please. The risk evaluation process is an incremental and iterative process. So the methods that we're developing here may be used in the future as appropriate for different chemicals. That's one of the reasons why we spend so much time asking questions about methodologies so that we can improve our strategies and our assessments overall. But keeping in mind that we're time bound, that the risk evaluations must be completed within 3 years of the publication of the scoping documents. The risk evaluations ultimately land on a determination of risk, whether that be no unreasonable risk or an unreasonable risk for a chemical. If the EPA determines that there is unreasonable risk for a chemical, even with one condition of use, we must move to risk management. And the risk management phase is where we impose restrictions in order to eliminate or minimize that unreasonable risk. Next slide, please. In order to ensure the highest quality science and transparency, we go through several rounds of various internal and external reviews. Some of our internal review processes include peer review with technical teams right here within our existing chemicals risk assessment program, and then continuing on to our senior scientists and management reviews. We also work collaboratively with other offices within EPA and sometimes those external to the agency. With this evaluation, we've collaborated specifically with EPA's Office of Research and Development, Office of Water, and Office of Air and Radiation, seeking early guidance on methodologies and feedback. And of course, our external review process includes a public comment period, and then continuing on to various processes such as the SACC, or it is in the case of other existing chemical evaluations, consulting with the HSRB, NASEM, and others as well. We also rely extensively on journal publications and then contract reviews and letter peer reviews, as you've seen in our other evaluations. Stakeholder engagement from various entities is also key, whether it be from the manufacturers of existing chemicals or from other stakeholders, as well as from NGOs. All right, next slide, please. So what will we do with this feedback and why are we seeking it? We're asking for the feedback to help us decide when and how EPA uses different approaches to estimate potential exposures to chemicals, define the conditions when specific approaches can or should be applied to the risk evaluations, and then also to assist the agency in quickly identifying readily available data best suited for use in risk evaluations. As you see with some of the future-oriented charge questions that we're asking here, future steps in the method development and utilization in ongoing and future risk evaluations are also important. That's all I have today. Thank you very much for listening.
Thank you for working through that and sharing the process with us. I think questions would come after the next presentation. So at this point, we'll move to Dr. Burris, who's going to give us an overview of the human health hazard assessment.
Thank you, George. My name is Janet Burris, and I am an environmental toxicologist in EPA's OPPT existing chemical risk assessment division. I am the assessment lead for the 1,1-dichloroethane risk evaluation. I'd like to express my appreciation to the members of the SACC for their participation and feedback. I would also like to thank the public commenters we will be hearing from as well. I will be providing you with a brief introduction to 1,1-dichloroethane, as well as an overview of the structure of the 1,1-dichloroethane risk evaluation document and the 1,2-dichloroethane human health hazard technical support document. Next slide. One dichloroethane by nature is a colorless, oily liquid with a chloroform-like odor. It is primarily used in organic chemical manufacturing as part of a process for making other chemicals. While it is volatile, it is also soluble in water, and a portion tends to stay in water if released to water. It is produced in the United States only, and the total production volume reported during the time period assessed was between 100 million to 1 billion pounds. While the primary use for 1,1-dichloroethane, as previously stated, is as a reactive intermediate, it is also occasionally used commercially as a laboratory chemical. It is not, EPA did not identify any general uses by the public or consumer uses. Next slide. This diagram shows all the parts of the risk evaluation. And you can see the parts this is a very large document, as you've experienced, over around 900 pages, with including appendices with about 30 plus supplemental files. However, we will only be posing charge questions or have posed charge questions on certain parts of the document. And you can see those highlighted in blue here. So there are certain parts of the risk evaluation document that do not have an associated charge question. So the parts of the risk evaluation document that we are asking for assistance with from the SACC are the systematic review process, the environmental exposure assessment and related analog selection, occupational exposures, the human health hazard assessment, including a discussion of the particular studies employed, associated appendices, and supplemental files related to those subjects. Areas where we are not asking questions about are excluded because the analyses presented there conform to previously established and peer-reviewed risk evaluation practices. Because we are not posing any charge questions on the topics not highlighted in blue, we will also not be addressing these topics in our following technical presentations today as the first day of the SACC panel meeting. However, comments on the entirety of the risk evaluation are always welcomed. Next slide. So why are we discussing 1,2-dichloroethane as well? This is the map of what will be the 1,2-dichloroethane risk evaluation. And a portion of that document we have charged the SACC with reviewing as part of this virtual panel. And that is the 1,2-dichloroethane human health hazard technical support document. That is because EPA is employing a read-across approach using 1,2-dichloroethane as an analog for 1,1-dichloroethane due to the fact that there are absent information on human health hazard and toxicity for 1,1-dichloroethane. Next slide. EPA is seeking early feedback on these approaches used in this as part of the SACC panel review of the 1,2-dichloroethane human health hazard assessment, and seeks input on both of these documents based on the charge questions. And next slide. Thanks for your attention. And I hope that we have a productive SACC panel discussion.
Thank you for the presentation. Now I will turn it over or open it up to the committee if there are questions about the two presentations that we've just heard from EPA folks. That's kind of unusual that we don't have any questions. But if we do not, I guess we can move on to the next presentation. And that would be from Dr. Orientis. And I apologize for going through that so quickly. I'm sure that you folks anticipated a little break there for a couple of questions, and so
That's perfectly fine. Thank you.
okay.
Dr. Cobb.
Yeah, I see you're ready. I'm going to turn it over now.
Thank you. Hello, my name is Neria Rentis, Exposure Assessor in EPA's Office of Pollution Prevention and Toxics, and I'll be presenting EPA's methodology for estimating environmental exposures. Next slide. This graphic presents the inputs and elements used in estimating environmental exposures and risk. Facilities report chemical emissions to air and discharges to surface waters via several EPA programs, such as the National Pollutant Discharge Permitting System's discharge monitoring reports. EPA then identifies the receiving water body and estimates the aquatic exposures by modeling concentrations of the chemical in the water column for water and sediment. The aquatic hazard threshold or concentration of concern is compared to the exposure concentrations, and the corresponding risk quotient is estimated. Next slide. For 1,1-dichloroethane, facility-specific data was available. That is, facilities have reported releasing 1,1-dichloroethane to surface water, and EPA identified the reported receiving water body hydrologic specific flow data using the National Hydrography Dataset, NHD+, to estimate the 1,1-dichloroethane concentration at the point of discharge. To consider the variability in releases, EPA collected 5 years of annual release data and used the highest release across those 5 years and a low receiving water body flow metric as a conservative estimate of aquatic exposures. One exception is a facility located in Westlake, Louisiana, where the second highest annual release in 2016 was used, as the highest annual release identified in 2020 was driven by a release that occurred during a storm event and, per discussion with the facility, does not represent normal operating conditions. Next slide. This slide shows in greater detail the Westlake facility releases across a number of years. The facility provided this data to EPA to show that during storm events, releases are much higher than normal. In reviewing these releases, the fluctuations in annual releases are significantly higher for this specific facility when compared to other facilities releasing 1,1-dichloroethane, as the storm events occur more than once across 5 years. Next slide. This slide shows the location of the Westlake facility by the Calcasieu River and releasing into Bayou Verdine. This location has unique features regarding the presence of bayous and is in an area with concentrated presence of chemical manufacturing and processing facilities. Next slide. Thank you for your attention.
Thank you for that presentation. Are there questions about the exposure assessment aspects of the documents that we're going to be reviewing?
I have a question.
Please.
This is Allison Jenkins. You talked about aquatic life, but could you describe what was assumed for the surface water releases and then drinking water exposures?
Yes, the question was, what did we estimate? I'm sorry, can you repeat the question?
Yes. Was the same methodology used for humans drinking water from these releases?
No, it was not quite the same methodology. Well, actually, a more higher tiered approach was used for drinking water. So what I described was estimating the concentration at the point of discharge. What we did for drinking water exposures, we then compared to or searched for intake locations, drinking water intake locations, and calculated dilution to those drinking water intakes. Now, to be clear, not every releasing facility has a corresponding or a downstream intake. There are quite a few industrial facilities that do not discharge to downstream intake, drinking water intake locations. Does that answer your question?
Yes. Thanks.
Right. So thank you for that question and answer. Dr. Graham.
Thank you for the presentation. My question is, did EPA receive any actual monitoring data for those water bodies to compare to their modeled results?
So we do have drinking water monitoring data. They did align with modeling results. In terms of receiving water body monitoring data, we did not identify monitoring results that were temporally and spatially aligned with the releases. So what we rely on is the effluent data, which is reported, and we can kind of assume that is monitoring data that's required by discharge permits. So we consider that monitoring data as well. It's just the effluent concentrations, however.
Thank you.
Yes, thank you for that question and that answer. Those are the kinds of questions that I also had as well. Dr. Landis.
Thanks for the presentation. I do eco stuff, so my questions are slightly different. Do you have any information on any sediment concentrations or any subsurface flow? So I noticed a lot of these areas are near coastal regions where I assume there's all kinds of interesting flow regimes as far as fate and transport. Do you have any information regarding that?
No, we do not have specific monitoring data. You're talking about sediment concentrations within these receiving water bodies.
Right, right.
Either in the bayou or other relevant locations. And again, they are not temporally aligned to the releases, if you see what I mean. So,
yes, I understand.
okay.
And this is especially for the exposure part, what kind of, I understand the bayous and stuff, the subsurface flow can be a bit different than in other areas, but do you have any information on subsurface flows and exposures due to that at these sites?
At these sites, there's limited data on 1,1 or a lack of data on 1,1-dichloroethane. We did consider through modeling, though,
right.
Our sediment concentrations and pore water concentrations. So we did higher tier modeling to account for those concentrations relative to the water column.
That's great. And I don't remember, of course, I've been reading a lot of this stuff. I don't remember those being in the report. That information being in the report.
It's described in the it should be just, it's described within environmental exposures. The model is called point source calculator. And that was specifically utilized and described in that section.
I understand that not everything that comes out in the calculator, not all the information will end up in a report. It's already pretty long. Thank you very much.
Okay, sure. Thank you.
All right. Thanks for that great discussion. Dr. Lee.
Okay, so thanks so much for the presentation. So I do have a question. So you mentioned high release associated with a storm event in a specific location, and probably that's it because a leak or overflow or something. So I think this is more like an accidental release. So my question is, does EPA has the information on whether the facility have planned to prevent a future accidental release or leak or overflow in the future when there's something similar to the storm event?
Understanding is this is the facility process and operations during a storm event. So I believe there's a retention pond, and as you're saying, there's a weir and an overflow. However, it's that's something that we're asking, is this really accidental? Or is this, part of planned events? Given the frequency of storm events, is this something to foresee?
Yeah. Thanks.
I see Dr. Landis' hand again.
Sorry, this is really useful. My other question is, these are all based on past data, which I understand that that's going to have to come from the past. In my committee work, several of my colleagues on our committees have asked about climate change, which in some of these low-lying areas is already apparent. And for making future regulation, they could be important. Are we to consider, or how would you want us to consider climate change and the expected changes in the amount of water, the sea level rise, and so forth, when we're trying to consider what potential exposures could be and therefore the potential effects? Because I haven't seen any information on that. And also living in a coastal area in the Northwest Pacific coast, I know that's a big management issue right now. So how, and you may not be the exact person, but I'd like to get it out there for our committee. How are we going to deal with the rising rising water and the projected storm events, especially in the South Gulf, in the Gulf area? Thank you.
So, Dr. Landis, those are good points. I believe they're exactly what we presented in the charge question for consideration.
Yes, so we can, yeah, I think we want to consider it, but as you know, there's a paucity of information. And I guess my interest is exactly what the kind of targets you are that you're trying to hit with this. Because the current information we have is not really addressing those issues. I also have just been working a lot with climate change, and I know it's a challenging modeling environment. I'll put it that way. Thank you.
Yeah, and this is George Cobb, to put this a little bit in context, I'm gathering that the question that Dr. Landis is asking is exactly what EPA is asking us. What information may be out there? What are our recommendations for how to handle those future scenarios relative to these types of risk assessments? I see Dr. Lowitz. Are you trying to comment, or did you just have your camera on?
No, I was gonna say what you just said, that, it feels like that Dr. Landis's comments are relevant for for our charge, and we're looking forward to hearing those comments.
Excellent. So it looks like we're thinking the same way this morning. Okay, I see Dr. Engel has his hand up.
Yes, thank you, Bernie Engel. You partially answered the question in response to Dr. Lee's question, but I'm still curious. I think, and I don't maybe have the words quite right. You indicated that the largest release that you excluded ultimately occurred during operations that were not normal or something to that effect. Can you help us understand that a bit more? So, was there something truly unusual? So it's just a bit vague in my mind.
Yes, that's correct. Is it really unusual? Well, it's unusual in terms of large concentration and large release. And it did coincide with Hurricane Laura. And so it's, as I showed in one of the slides, there across several years, there's several events that have occurred, and they do coincide with larger volumes of release.
Maybe a quick follow-up. Was there any additional unusual that occurred in combination with the hurricane? I guess that's the underlying question to my question. So is it just the hurricane that was unusual, or is there something further that combined with the hurricane that made it extraordinarily unusual?
I'm not sure that was clearly described by the facility. It's what they report to EPA is a large pollutant load of 1,1-dichloroethane.
Okay. Thank you for that discussion. I have another follow-up to that same scenario, and want to make sure, because it frames how the comment would come to this to your charge question or the response. So you've got this high release, and it's relative to a storm event. Is that right? It's relative to a high rain event. And what you're saying is, what EPA is saying, this rain event would not coincide, this discharge would not coincide with a low flow estimate, which we are using in our modeling efforts. So we're going to exclude that because it couldn't exist during that low flow time regime. Is that fair?
It's not, a low flow regime would not be reflective of those conditions.
Correct. Okay.
So, correct. I think you've captured it correctly.
So as a ground truth, so to speak, could you use not a low flow, but perhaps a higher flow closer to what you have, and just see what the model spits out to say, well, this would be the estimated exposure, not at that low flow condition, but at a higher flow condition? Could you not use that as a kind of a bounding exercise?
I think, yes, thank you for that comment, and I'll refer you back to the charge question. But,
okay.
Yeah.
All right, that's fine. So are there other questions for EPA? If not, thank you. That was, wait, I see one more. Dr. Hernandez.
I have a doubt regarding this part. It is possible to connect the TRI data that you collected with the risk management plan data and identify if after those accidental releases, the facility reported something regarding to a management plan for preventing this kind of accidents.
I'm not sure these are considered accidental releases. And that is, again, related to the charge question.
Thank you for that comment. And not to belabor the conversation, the SACC was pretty clear in earlier reviews that even if these releases are accidental, they need to be considered because that is part of use in commerce. So that's one of the things the SACC was pretty clear about a few years ago. So with that, I think we can move on to our next presentation. Thank you so much for that presentation and that discussion. That was very helpful. And so now Dr. Brennan is going to talk to us about environmental hazard read-across approaches.
Good morning. Can everyone hear me?
Yes.
Good morning. I'm Jennifer Brennan, a biologist with US EPA, and I'll be covering the information pertaining to charge questions 2A and 2B, which address the environmental hazard read-across approach used in the 1,1-dichloroethane draft risk evaluation. Next slide, please. Some context as to why read-across was used for the environmental hazard portion of the draft risk evaluation. Few empirical data were reasonably available on aquatic species for 1,1-dichloroethane. For example, the initial aquatic data set consisted of a single 1-hour respiratory study in fish exposed to 1,1-dichloroethane. Additional studies identified during development of the draft risk evaluation from the Japanese National Institute of Technology and Evaluation, known as NITE studies. These provided additional 1,1-dichloroethane aquatic hazard data. However, the 1,1-dichloroethane aquatic hazard data set still was not comprehensive across aquatic taxa and exposure durations. Therefore, EPA used 1,2-dichloropropane and 1,12-trichloroethane data to supplement the aquatic and benthic hazard characterization for 1,1-dichloroethane. Next slide, please. A bit more detail on how the analogs were used in the environmental hazard read-across. 1,2-dichloropropane was selected as an analog for read-across of aquatic environmental hazard data, specifically fish, mysid, and algae, to supplement the 1,1-dichloroethane aquatic environmental hazard. Another approach EPA used to add additional taxa representation for the aquatic hazard was a combination of 1,1-dichloroethane and analog 1,2-dichloropropane acute aquatic vertebrate and invertebrate hazard data to generate web ice toxicity predictions using US EPA's web ice program. And these added additional aquatic taxa representation, such as benthic invertebrate and amphibians for acute hazard. No chronic benthic hazard data were reasonably available for either 1,1-dichloroethane or 1,2-dichloropropane. Therefore, 1,12-trichloroethane was selected as an analog for read-across of chronic benthic environmental hazard to 1,1-dichloroethane. Next slide, please. The table in front of us describes how the analog data were used to derive environmental hazard thresholds in the draft 1,1-dichloroethane risk evaluation. The first column describes the type of environmental hazard threshold: acute aquatic, acute benthic, chronic aquatic, and so forth. And the second column describes whether that environmental hazard threshold was sourced from 1,1-dichloroethane data, a combination of 1,1-dichloroethane and analog data, or whether analog data alone were used for that environmental hazard threshold. And of note, again, the acute aquatic and acute benthic exposure was from a combination of 1,1-dichloroethane and 1,2-dichloropropane data, whereas the chronic benthic exposure hazard threshold was from 1,12-trichloroethane data, and the algal hazard threshold was from 1,2-dichloropropane analog data. Next slide, please. Now moving into how the analogs were selected for the environmental hazard read across. Several lines of evidence went into the analog selection for environmental hazard, this being structural similarity between 1,1-dichloroethane and its analogs. A number of different structure programs were used to assess structural similarity, and screening thresholds were applied. The second line of evidence in the analog selection for environmental hazard was comparing physical, chemical, environmental fate, and transport similarity between 1,1-dichloroethane and its analogs. An initial screening in this line of evidence was conducted using log KOW screen, plus or minus 1 log unit between 1,1-dichloroethane's log KOW and the analogs log KOW, as well as a screening by vapor pressure. So screening the vapor pressure of the analog within 10-fold of that of 1,1-dichloroethane's vapor pressure. Additionally, the assessment of whether the analog had aquatic and benthic hazard data to be used in the read across was checked at this point, and whether those data had been reviewed using systematic review approaches. A third line of evidence that went into the analog selection for environmental hazard was the ecotoxicological similarity comparison between 1,1-dichloroethane and its analogs. And for this line of evidence, 2 comparisons were done. The first being a predicted hazard comparison using US EPA's EcoSAR program. And a second comparison was done using empirical hazard that we did have for 1,1-dichloroethane for aquatic hazard against the empirical hazard of its analogs. Next slide, please. This flow diagram in front of us is a visual representation of what I described on the previous slide. So again, this is a 3-part process with the analog selection, starting with structural similarity comparison in the top left. So as mentioned, a number of different structure programs were used to assess structural similarity of the analogs to 1,1-dichloroethane, specifically US EPA's analog identification methodology tool, the OECD QSAR toolbox, US EPA's cheminformatics search module, as well as US EPA's Generalized Read Across, or GENRA, program. Screening thresholds were applied, analogs were compiled, and analogs that met the screening thresholds in 3 out of these 4 structure programs were then moved into the second line of evidence for analog selection, which was the comparison of the physical, chemical, environmental fate, and transport properties. Again, screening by log KOW of the analog against that of 1,1-dichloroethane was done within plus or minus 1 log unit, as well as a screening by vapor pressure within 10-fold of the analog's vapor pressure to that of 1,1-dichloroethane, since 1,1-dichloroethane is a volatile chemical. Again, the analog having the aquatic and benthic hazard data appropriate for use in the read across was checked, and whether those data had undergone systematic review approaches. And at this point, analogs moving forward from that process were subject to a more full comparison of the physical, chemical, environmental fate, and transport properties to better assess similarity in water and in sediment between 1,1-dichloroethane and the analogs. Moving into the third line of evidence, which is the ecotoxicological similarity. Again, we have the predicted hazard comparison, which was the first comparison made for this line of evidence using US EPA's EcoSAR program, which can generate toxicity predictions for a number of different aquatic taxa, such as fish, aquatic invertebrates, as well as green algae for both acute and chronic exposure durations. Those EcoSAR predictions for 1,1-dichloroethane and its analogs were compared plus or minus 10-fold. And then the second comparison that was done for ecotoxicological similarity was using empirical hazard evidence that we had for 1,1-dichloroethane aquatic hazard to that of its analogs. And then finally, analogs were selected for the environmental hazard read across. Next slide, please. These are the results of the structure similarity comparison between 1,1-dichloroethane and its analogs. Specifically, these are high priority substance chlorinated solvents that are shown as the analogs here for 1,1-dichloroethane, 1,2-dichloropropane, 1,12-trichloroethane, and 1,2-dichloroethane. And as mentioned, 4 different structure programs were used to assess the structural similarity between 1,1-dichloroethane and these analogs. In the analog identification methodology tool, or AIM, whether the analog was a first or second pass analog of 1,1-dichloroethane was checked. And you can see that all 3 of these chlorinated solvent analogs are second pass analogs of 1,1-dichloroethane. In the OECD QSAR toolbox, using the Tanimoto-based PubChem fingerprints, a screening threshold of 0.5 or above was used to assess structural similarity. And you can see that all 3 of these chlorinated solvent analogs do exceed a score of 0.5 using that analysis in the OECD QSAR toolbox. Using the Generalized Read Across, or GENRA program, chemical Morgan fingerprints were used and the top 100 analogs were pulled. In this program, a screening threshold of 0.1 and above was used to assess structural similarity, and you can see that 1,2-dichloropropane meets that criteria for GENRA. In the cheminformatics search module, a Tanimoto coefficient was used in the search module to obtain analogs for 1,1-dichloroethane. And you can see, again, using a very similar score to the OECD QSAR toolbox, 0.5 screening threshold and above, that both 1,1,2-trichloroethane and 1,2-dichloroethane exceed that threshold for structure similarity using the cheminformatics search module. As mentioned in the flow diagram, looking across these 4 programs, EPA was looking for concordance in structure similarity in 3 out of the 4 programs that were used here. And you can see that all 3 of these chlorinated solvent analogs meet that threshold of 3 out of 4 programs for structure similarity. Next slide, please. Now moving into the physical chemical similarity of 1,1-dichloroethane and its analogs. Since 1,2-dichloropropane, 1,1,2-trichloroethane, and 1,2-dichloroethane met the structural similarity line of evidence, they've moved forward now into this second line of evidence in the analog selection for environmental hazard. Again, initial screening by log KOW plus or minus 1 unit, log unit of the analog to that of 1,1-dichloroethane was done. And you can see, looking at the log KOW of these 3 chlorinated solvent analogs to that of 1,1-dichloroethane, it's well within plus or minus 1 log unit and is very close in value. Second screening by vapor pressure within 10-fold of 1,1-dichloroethane's vapor pressure was done. Again, all 3 chlorinated solvent analogs are within 10-fold of that vapor pressure screen. Of note, 1,2-dichloropropane and 1,1,2-trichloroethane do have lower vapor pressures than 1,1-dichloroethane by a bit. They're on that lower end. This is described as an uncertainty in a later slide in this presentation, as well as how EPA addressed that uncertainty in the read across. Backing out and looking at these additional physical, chemical, and environmental fate and transport properties across these 4 chemicals, we are seeing a picture of fairly water-soluble chemicals with low log KOW, low log KOC. They will not bind to sediment or soil very well. We have low bioaccumulation and low bioconcentration factors, not very bioaccumulative. They are volatile. They will likely volatilize out of the water well before hydrolyzing in the water. All have very similar molecular weights and all exist as a colorless liquid at room temperature. Next slide, please. Now moving into the results of the ecotoxicological similarity line of evidence between 1,1-dichloroethane and its analogs. Again, the predicted hazard comparison was the first comparison made for this line of evidence using EcoSAR. And these generate toxicity predictions for both the acute and chronic exposures to fish, both fresh and saltwater, aquatic invertebrates, both fresh and saltwater, as well as green algae. And this first comparison was made between 1,1-dichloroethane and the analogs 1,2-dichloropropane, 1,12-trichloroethane, and 1,2-dichloroethane. And if we look at the table at the bottom of this slide, this table shows an average ratio of the analogs EcoSAR toxicity predictions divided by that of 1,1-dichloroethane's toxicity predictions from EcoSAR. A number less than 1 indicates that the analog is protective of 1,1-dichloroethane. A ratio of 1 or very close to 1 indicates almost identical toxicity predictions between analog and 1,1-dichloroethane. And a ratio greater than 1 indicates that the analog is less toxic than 1,1-dichloroethane by prediction. So looking across for 1,2-dichloropropane, its ratio of predicted toxicities to 1,1-dichloroethane indicates that 1,2-dichloropropane will be protective of 1,1-dichloroethane. For 1,12-trichloroethane, its EcoSAR predictions agreed very well, as you can see from the ratio of very close to 1. For 1,2-dichloroethane, its EcoSAR toxicity predictions were predicted to be almost half as toxic as 1,1-dichloroethane's toxicities. Therefore, at this point in the read across, 1,2-dichloropropane and 1,12-trichloroethane moved forward for the empirical hazard comparison to 1,1-dichloroethane, but 1,2-dichloroethane did not move forward for this second comparison. Next slide, please. Now looking at the measured hazard comparison for aquatic taxa for the data we did have on hand for 1,1-dichloroethane compared to those of its analogs. So again, what we're looking at in the first two columns are species and duration of exposure as well as the endpoint. And if we look across a row, the data for that species and exposure duration for 1,1-dichloroethane and its analogs may have come from a single study, or those data may have been sourced across multiple studies. However, it's still the same species and exposure duration and endpoint that is being compared in that row. Looking at the ratio of 1,2-dichlooropropane's empirical hazard to 1,1-dichloroethane's empirical hazard, we are seeing ratios generally less than 1, indicating that 1,2-dichloropropane will be protective of 1,1-dichloroethane hazard. For 1,1,2-trichloroethane's ratio of empirical hazard to 1,1-dichloroethane, we are generally seeing ratios less than 1. So at this point in the read across process, given the lines of evidence of structural similarity between 1,1-dichloroethane and its analogs, the similar behavior in aquatic and sediment media from a physical chemical standpoint, the empirical hazard comparison in front of us, as well as that predicted hazard comparison on the previous slide, 1,2-dichloropropane was selected as the primary analog for aquatic hazard read across to 1,1-dichloroethane. And 1,1,2-trichloroethane was selected for benthic hazard read across to 1,1-dichloroethane. Next slide. This slide describes uncertainties in the environmental hazard read across. One uncertainty is that relatively small chemical structures of 1,1-dichloroethane and its analogs could result in lower structural similarity scores, as there is just not a lot of a chemical there for comparison on a structural standpoint. EPA addressed this uncertainty by looking for concordance across multiple structure programs rather than relying on one structure program. Another uncertainty in the environmental hazard analog selection, lower vapor pressure of analog candidates 1,2-dichloropropane and 1,1,2-trichloroethane relative to that of 1,1-dichloroethane, although still within tenfold, could result in volatility differences between target and analog. EPA addressed this uncertainty by factoring in experimental design consideration in the analog's empirical hazard data set. So measurement of the analog chemical over the exposure duration of the study, use of flow through or semi-static renewal in the analog empirical hazard that were used in the read across. And of note, the difference in the vapor pressure is that the analog vapor pressure is lower than that of 1,1-dichloroethane. Where these experimental design considerations become absolutely critical is if that difference were reversed and the analog was more volatile than 1,1-dichloroethane. Another uncertainty in the read across is that EcoSAR hazard predictions do not include a prediction for a benthic invertebrate. However, EPA addressed this uncertainty in that the ability to read across to benthic hazard was inferred from similar physical, chemical, and fate properties of 1,1-dichloroethane and 1,12-trichloroethane relative to sediment, as well as similar hazard between 1,1-dichloroethane and 1,12-trichloroethane in aquatic invertebrates. Next slide, please. Conclusion and key points. 1,1-dichloroethane is relatively data poor for aquatic and benthic hazard. An analog selection was performed to supplement 1,1-dichloroethane's aquatic and benthic hazard data set. Similarity analyses for both structure as well as physical chemical behavior and water and sediment indicated 3 high priority substances, 1,2-dichloropropane, 1,12-trichloroethane, and 1,2-dichloroethane as suitable analogs for 1,1-dichloroethane. Further comparison for ecotoxicological similarity indicated 1,2-dichloropropane as the most suitable analog for read across, followed by 1,12-trichloroethane. Therefore, 1,2-dichloropropane was selected as the analog for supplementing 1,1-dichloroethane's aquatic hazard data set, and 1,12-trichloroethane was selected as the analog for supplementing 1,1-dichloroethane's benthic hazard data set. Next slide, please. And thank you for your attention.
Right. Thank you for that thorough presentation. So at this point, I think we have time for, are we taking time for questions now? Yes. So let's see if there are questions from the committee. I see several hands. Dr. Stice first.
Yes, I was wondering what the rationale behind the selection of the 4 computational toxicology tools were. The rationale was not provided in any of the documents, and there are some issues with 2 of the 4 tools employed for analog selection. AIM has not been supported by EPA or updated since 2012, and EPA itself direct users of the tool to use Genera instead another tool that you use. Also regarding Chem Informatics module, your website states that it is still under development, but it is available for external stakeholders to use in order to provide feedback early in the development process. So knowing these things, I was just wondering what the rationale was behind selecting these 4 tools for analog identification.
Thank you for your question, Dr. Stice. The rationale for selecting these 4 tools, so AIM is very commonly used in the Office of Pollution Prevention and Toxics, especially on the new chemicals side of risk assessments, and OECD QSAR toolbox as well. So those 2 are on our TSCA list of NAMs. And so that was the rationale for those 2 programs being selected for this analysis. For the Chem Informatics search module, as well as Genera, those are US EPA programs, publicly available. it was important that these programs do be publicly available to others if we are using them in this draft risk evaluation. So that's a bit behind some of the rationale of why these 4 programs in particular are used in the draft risk evaluation.
Just a second. Why I do understand that rationale, I still feel it's lacking because according to EPA, you have not updated AIM since 2012, and you do not intend to support any updates to that tool. And also it seems that the chem informatics module is still under development. And my other question is that have you considered using additional computational toxicology tools to overcome some of these shortcomings when it comes to selecting these 4 specific tools?
Thank you, Dr. Stice. Absolutely, if the SACC has additional recommendations on appropriate tools to be used in the read across in that first line of evidence for structural similarity or any of the lines of evidence, please, we are interested in this feedback, which is why it's a charge question.
Excellent. Yeah, excellent. Thank you for that response and the question. Dr. Graham.
Thank you for that presentation. My question, and I have to apologize in advance because I really didn't read that section. I'm not on those charge questions, but I have used ECOSAR, and I know that it is not appropriate for every chemical. And wondering whether you had any actual data to compare the ECOSAR results for 1,1-dichloroethane with, the actual results with the results from ECOSAR.
Absolutely. Thank you, Dr. Graham. Yes, that comparison was made in the weight of the scientific evidence section, if you read, and I believe that's in one of the appendices. So comparison between the empirical and the ECOSAR hazard directly, as well as in the analog appendix itself in the environmental hazard read across. So yes, that concordance between empirical and predicted is also an important consideration.
Thank you.
Yes, thank you. Dr. Landis.
Thanks a lot. That was really informative. I am charged with answering those questions in the charge questions, and so I tend to have several questions. One, are we assuming that the mode of action is the same for each one of these chemicals? And is that narcosis, something that's fairly not site specific? Is that an assumption we're making as you go through and do the structure activity calculations and so on?
Yes, narcosis is being assumed in this case.
That's really, that really helps. When I was looking at the calculations and the predicting toxicity, let me back this up with a little preface. You talk a lot about uncertainty, but what you're doing is using the kind of uncertainty that's about lack of knowledge. We don't have toxicity tests and so forth, but not measurement uncertainty. So in your predictions, with the structure activity modeling, I don't see error terms associated with those. What those boundaries would be, like a 95% confidence interval or something else, where they've gone through their models and they've compared what they've estimated to what it's actually been measured to be. Mm-hmm. And I don't see those for those different kinds of models. And I think those would be really useful to have. I want to know how close those estimates are and what the expectation is for the calculation, the predicted error would be. I didn't see that. Do you have that information?
Thank you, Dr. Landis. I believe ECOSAR does not give error around the predictions. That is something we could take into consideration as that is, part of model development.
Right. And early in my career, I did lots of QSARs, and that was always one of our most important considerations, to have that as tight as possible to reduce that kind of uncertainty. That relates to another question I have about empirical uncertainty. In your estimates of ECV, you have several EC50 values listed. There's an EC value that's from a regression. All regressions have confidence intervals. Again, another measure of empirical uncertainty. And they must have them, but they weren't reported. Is that why they're left out? Or and a lot of EPA stuff and a lot of everyone's stuff I see, people give an EC50 value, but not the confidence interval. Do you have confidence intervals for that information? Because it becomes important later on when they use a lot of this information to do the SSDs. So do you have that information? Can you really give me an estimate on what kind of that uncertainty is in those toxicity tests?
Those empirical studies could be checked to see if they do have confidence intervals.
So if they've done the calculation, you can calculate the confidence intervals. Whether or not they did it, which is actually trivial these days, yeah, that would be really helpful, because one of our charge questions is, dealing with the SSDs and all those estimates. That'd be really, really useful. I think that's really good to know. I guess I'd hate to request things. How should I put it? That kind of information would be really valuable in trying to evaluate the rest of the analysis there. So I'm trying to get that feedback because I have to answer these questions by the end of the week. Thank you very much.
Thank you, Dr. Landis.
Thank you. And now Dr. Rose.
Thank you. So this is Jane Rose. I just had a point of clarification on the slide that showed the structural similarity, and looking at a number of the analogs on the Genera tool output. I was just curious whether, and there was a dash, so you didn't show any kind of structural similarity score. I was just curious if these were below the threshold of 0.1, or they weren't part of the top 100, or the chemicals weren't in the database as part of the selection of analogs. Yeah, exactly.
That's a good question, Dr. Rose. Thank you. So we do happen to know the scores for those two chemicals using various other filtering parameters, but they are not appearing in the top 100 for this list. So that's why they have dashes there.
Got it. Okay, thank you.
Yes, thank you for that question and the answer. And yeah, those are the kinds of things that we can point out in the document or in our response that maybe could be improved. So that's a good point.
Mm-hmm.
Okay, so Dr. Brennan, I think that's all for your part. Now we have a decision to make. We're pretty far ahead of schedule. We were scheduled for an early lunch break on my agenda. I think I'll ask Dr. Burris if you think we can do your part and Dr. Irving's part before lunch, or if you would prefer to take a break now. And I'll ask you, Janet Burris, what you think about that. Is there?
Okay. Thank you, Dr. Cobb. We can go ahead and continue if you'd like. I know that I can get my part in, and possibly Williams. Do you think you can?
I'm not necessarily worried about the 11:40 timeline. I'm just wanting to make sure that your people are available, that we're not getting the schedule too sideways for y'all if we go ahead with your part and Will's part next.
We're flexible. So the part that William is going to be covering is about 40 minutes, and mine is just an introduction to that. So we're looking about, 50 minutes. So that would make it a much later lunch break. I don't
Okay.
know what schedules are for your team on that end, so.
Well, let's at least go ahead with your part, Janet. And I know that's not as logical a break, but I'd like to get through as much as we can. And the folks on the West Coast, it's still breakfast time for them. So,
Yeah.
So if we can go ahead with yours, and then we'll
All right.
assess after that.
Okay.
Thank you.
All right, so again, my name is Janet Burris and I am from EPA and OPPT, the Ecological Risk Assessment Division. And I'm the lead assessor for 1,1-dichloroethane risk evaluation. I'll be providing you with just an introduction to the human health hazard assessment for 1,1-dichloroethane. And that pertains in particular to TSCA's systematic review process. So next slide, please. So this diagram provides an overview of the process that was used by the team to identify literature information and evaluate the literature information in a systematic process. These steps are pertain to other parts of data that was used in the risk evaluation, but we're in particular discussing the human health hazard data or the application of this review process to the human health hazard data in particular. So the systematic review process is composed of a data evaluation step first. It's a first step in screening where you apply predetermined data quality evaluation criteria to on-topic literature after initial on-topic literature screen. And that data evaluation results are provided in a supplemental file. Next, you proceed to data extraction, where you extract the results from the on-topic literature to consider for use in the risk evaluation. That information on data extraction is provided as a supplemental file in the draft RE. The data extraction is followed by evidence integration, where you evaluate the weight of the scientific evidence for each, typically for each organ system, both within and across evidence streams. And that's integrated and followed by a dose response analysis. And this is where you derive PODs for endpoints with adequate quantitative data for organ systems demonstrating adverse effects. So points of departure is what POD means. And then these PODs are used for comparison to exposure estimates to evaluate risk. So that's the general process. We did complete this full systematic review process for 1,1-dichloroethane for human health hazard, animal data, as well as epidemiology information that was available. And as we are going, you're going to hear later from William, we did use a read across approach as well for human health hazard. As we went through the systematic review process, the data that was identified for 1,1-dichloroethane was not suitable, very sparse, and not suitable for dose response analysis. So we moved again to identifying an appropriate analog for 1,1-DCA, and you'll hear that in William's following presentation. So next slide. So again, the OPPT systematic review process, it does include a full data evaluation of studies within existing assessments that may have been made or available from other EPA programs or other federal programs. It captures studies that are also captured by these programs. And that passed the initial title abstract screening and underwent the full text screening phase of the systematic review and data evaluation. So a summary of the studies not considered or considered suitable for identification of PODs and dose response assessment for 1,1-dichloroethane and 1,2-dichloroethane can be found in sections M.2.1, M.2.2 in the draft RE respectively. So what I'm describing here is that since we identified an analog, which was 1,2-dichloroethane, and you will see later how we arrived at that conclusion, we completed this systematic review process for 2 chemicals, both 1,1-dichloroethane and 1,2-dichloroethane. And this information is found in supplemental files. Next slide. So the 1,1-dichloroethane hazard identification and evidence integration based on the systematic review process did not identify adequate data for non-cancer oral and inhalation, and there were no data available for dermal exposure, dermal dose response assessment for all exposure durations, acute, short-term, and chronic. There were no adequate data for cancer by the oral route and no available data for cancer by the inhalation and dermal routes as well. So as you can, for 1,1-dichloroethane, the literature search and review process essentially yielded no usable information for derivation of dose response values. Data gaps were then filled by using a read-across approach from the identified human health hazard analog, which was 1,2-dichloroethane. And this was based, as you will hear more about in the next presentation, on an analysis of similarities of structure, physical chemical properties, metabolism, and toxicological endpoints, both non-cancer and cancer. So again, this necessitated our completion of the SR process, which includes hazard identification, data quality evaluation, data extraction, and evidence integration for both 1,1 and 1,2-dichloroethane. Next slide. Historically, offices across EPA and other agencies, such as ATSDR, have developed their own assessments for 1,1 and 1,2-dichloroethane. And you'll find in table 5-53 of the 1,1-dichloroethane risk evaluation for non-cancer, a comparison of these identified assessments. And they're compared by exposure duration and exposure route. EPA also reviewed the 1,1 and 1,2-dichloroethane toxicological profiles by ATSDR that were issued in 2015 and 2022 as a draft, respectively. We are aware that ATSDR finalized their 1,2-dichloroethane toxicological profile just this past July in 2024. As a brief mention here, our systematic review process includes data that was identified up until the year 2019 and earlier. EPA reviewed both 1,1 and 1,2-dichloroethane EPA's provisional peer-reviewed toxicity values assessments, or PPRTVs values as well. And 1,1 and 1,2-dichloroethane were not assessed for non-cancer exposure durations or routes by EPA's IRIS program. Next slide. And so the presentation provided next by William Irwin is going to describe the process for the selection of the analog based on similarities of structure, physical chemical properties, metabolism, toxicological endpoints, both non-cancer and cancer. And the use of analog and read across was necessitated by essentially the systematic review process not identifying adequate information for 1,1-dichloroethane.
All right, thank you for that presentation. I think we're exactly on our agenda, which is unusual. So I think perhaps we'll break at this point, and that does mean that questions will follow the next presentation. And so we will now take a break for 1 hour. And well, now it's 59 minutes. I've talked long enough. It's now 59 minutes. Let us reconvene at 12:40 Eastern, 11:40 Central, 10:40 Mountain, and 9:40. Is that right? 9:40 Pacific. Thanks, folks. Right. Welcome back. This is George Cobb, welcoming everyone back after our break. And before we go to Dr. Irwin from EPA, I'd like to see if our DFO has anything that we need to go over.
No, I think we're good. I'm just wondering if we're recording right now.
That's a good point. I cannot tell.
We are live on YouTube.
Okay, thank you.
All right. Thank you for getting all those things straight. So now we're going to hear from Dr. Irwin about human health read across, hazard assessment and read across.
Oh, Dr. Cobb, do we have to take a roll call? Or not?
Yeah. Yes.
You know
Roll
what?
call.
This is,
Yep.
I'm sorry. This is so early in the day that my brain doesn't have this as lunch.
All right. Yeah, you're a couple hours behind us. I understand. Yeah.
So I think technically we do have to have a roll call, which we'll have a long time after this with no roll call. So Dr. Apte.
Present.
Dr. Baker.
Here.
Dr. Fong.
Present.
Dr. Fox.
Present.
Dr. Gentry.
Here.
Dr. Graham. Thought I saw there, Cynthia. I see her.
I'm here. Sorry, I was on mute.
I see Dr. Heiger Bernays may be here this afternoon. No. Okay. Ms. Jenkins.
I'm here. Thank you.
Dr. Lee.
I'm here. Thank you.
Right. Dr. Merced Nieves.
Here.
Dr. Rumpler. Dr. Samuel. Mr. Wright.
I'm here.
Right. Dr. Engel. Dr. Engel. Dr. Hernandez.
Present.
Dr. Kalushny.
I'm here.
Dr. Landis.
Here.
Dr. Lynch.
Here.
Dr. Malberti.
Here.
Dr. Rose.
Here.
Dr. Stice.
Present.
Dr. Zeus still not with us. Okay, let's go back and pick up to see if, has Dr. Rumpler joined us? Dr. Samuel? Dr. Engel? Right, so I think that's it. Did I miss anybody this time?
Yeah, this is Stephanie. I'm here. I think you missed me because I said I have to leave early to go teach in an hour.
Oh, okay. Yeah, I have you X'd off for the afternoon, but you're here now.
Yes, I'm here for the next little bit. Thanks.
Excellent. Thank you. Anyone else?
Okay. How many SACC members are there for this session? So I'm trying to do.
I have 12.
Okay, great. Thank you.
Yeah, there's supposed to be a couple more, but they didn't answer. So
Okay,
we can check the screens when we're working through.
Okay, all right. We can continue. Thank you.
All right. So now we are to Dr. Irwin for the presentation of human health hazard read across.
Yes, thank you. Can you see me?
Yes.
Okay, do you want to see me? Okay. Anyway, okay, so I'm William Irwin, a toxicologist in EC-RAD. I will be presenting the process EPA used to identify an analog for 1,1-dichloroethane and read across for human health hazard for 1,1-dichloroethane. On behalf of the team, Kathy Anatol, Ali Shobhati, Philip Kaiser, and others. Thank you. So next slide. So adequate human health hazard data were not available to assess non-cancer and cancer risk for 1,1-dichloroethane. So EPA chose to use a read-across approach using data available for a closely related chemical or analog to evaluate human health, non-cancer, and cancer hazard of 1,1-dichloroethane. The analyses resulted in the identification of 1,2-dichloroethane, which is an isomer of 1,1-dichloroethane, as the most appropriate analog with acceptable and, very importantly, available data to fill data gaps. And the general principles for read across are outlined in the Zaraga et al. EPA 2019. And this paper was used to identify an analog for 1,1-dichloroethane and included structural similarity, physical chemical similarities, metabolic similarities, and toxicological similarities. So a lot of this is going to be very similar to the ECO framework that you heard about before. Next slide, please. So this slide shows the structural similarity scores for multiple read-across tools for various solvents considered for read-across analogs for 1,1-dichloroethane. Tools used for the analog identification methodology or AIM, the OECD QSOR toolbox, GENRA, and the hazard comparison dashboard, which is identical, it's synonymous with the chem informatics module that was described earlier. So for human health, if you look at the table, the best similarity scores to 1,1-dichloroethane were for 1,2-dichloroethane at scores of 0.63 to 0.79, and for 1,12-trichloroethane 0.27 to 0.79, and 1,2-dichloropropane at 0.42 to 0.75. So as you can see in the table, the score of 1 is perfect, and then the lower the score, the lower the similarity. So as you can see, some are considerably low. So next slide, please. So this slide lists the physical chemical properties for the top 3 analog candidates. Within testing area, the solubility analog KOW results are similar to one dichloroethane. However, vapor pressure of 1,1-dichloroethane at 227 millimeter mercury is much higher than that for 1,1,2-trichloroethane at 23 millimeters mercury and 1,2-dichloropropane at only 40 millimeters mercury, which and these 2 analogs also have substantially higher molecular weights than 1,1-dichloroethane. So this is very important for the biology of humans, mammalia. So in the animal studies for the 1,1-dichloroethane, most of the oral dose is eliminated through the lungs. This is really interesting. So these particular physical chemical properties are important for tissue distribution. So a weight of scientific evidence approach was utilized, and 1,1-dichloroethane and 1,2-dichloroethane have the most similar solubility, molecular weight, and vapor pressure information. Next slide. So this figure depicts the metabolism aspect of the ADME for 1,1-dichloroethane in vitro in rat microsomes in wild-type rats. So no human studies were located for metabolism. Some important metabolites that were identified are reactive species, a chloroaldehyde, which in this case is dichloroacetaldehyde, and acetyl chloride and hydrochloric acid. So also cellular glutathione is consumed in the clearance process. This is described in the ATSDR document, which we consulted regularly. So increased reactive species and decreased glutathione levels have been related to important health hazards. And so those are the metabolites that we focused upon. And the hazards, for example, could be DNA and cellular damage from these reactive metabolites. Next slide, please. So this figure depicts the metabolism of the analog 1,2-dichloroethane in vitro using rat microsomes again, and in vivo rodent data. And again, there's no human studies located for metabolism. So some important metabolites are the reactive species. Again, another chloroaldehyde. In this case, it's 2-chloroacetaldehyde. An episulfoniamide, which is notorious for being very reactive. And again, hydrochloric acid. And again, cellular glutathione is consumed in the clearance processes. So increased reactive species and decreased glutathione levels, again, they've been related to important human health hazards, again, cellular damage and DNA damage. So next slide, please. So this slide shows the metabolic similarities between 1,1-dichloroethane and 1,2-dichloroethane, which are concerned for hazards, as depicted in figures Appendix J1 and J2 of the 1,1-dichloroethane draft risk evaluation. In terms of metabolic similarities between 1,1-dichloroethane and 1,2-dichloroethane, both chemicals are directly reactive and both form chloroaldehydes, which can form persistent DNA crosslinks. And this is described in the OECD QSAR document from OECD in 2015. They also form various reactive species. They both produce hydrochloric acid and decrease glutathione levels. So increased reactive species, DNA crosslinks, and decreased glutathione levels have been related to important hazards such as cancer and cellular damage. Next slide, please. So this table lists many common cancer and non-cancer hazards and properties between 1,1-dichloroethane and 1,2-dichloroethane. Common hazards are irritation, narcosis, cardiotoxicity, genotoxicity, without metabolic activation, immunotoxicity, nephrotoxicity, hepatotoxicity, nutritional, metabolic toxicity, endometrial polyps, hepatocellular carcinoma, hemangiosarcomas, and mammary gland tumors. So one thing to consider, this is a table of qualitative similarities between the two chemicals and their hazards. An important point is that the dose response can be different for the various hazards identified. So both chemicals are dichloroethane isomers that are chemically reactive without metabolic activation. Next slide, please. So this slide lists common hazards related to cancer between 1,1-dichloroethane and 1,2-dichloroethane. Both chemicals produce mammary gland adenocarcinomas, hemangiosarcomas, and endometrial stromal polyps, which the latter is a precancerous lesion. So both chemicals have positive genotoxicity and immunotoxicity findings, which are recognized cancer mechanisms. Next slide, please. So this slide lists some cancer tools and resources utilized for the 1,1-dichloroethane risk evaluation. The EPA oncologic model is an expert system that mimics the judgment of human experts by following sets of knowledge rules based on studies of how chemicals cause cancer in animals and humans. So EPA Oncologic was developed by world-renowned cancer experts, Dr. Gintak Wu and Dr. David Lai. And there's a web link there for more information. Also consulted was the OECD Fundamental and Guiding Principles for QSAR Analysis of Chemical Carcinogens with Mechanistic Considerations 2015, which I referred to previously. An important point there is that bifunctional persistent DNA cross-linkers tend to have a higher potential for carcinogenicity. And so in this document, they discuss monofunctional versus bifunctional versus polyfunctional reactive groups and the distance between them and how that is considered. So substances that contain more than one electrophilic group tend to have a higher potential for carcinogenicity than those with only one electrophile functional group because of the possibility for DNA cross-linking. So the reactive groups can be identical, such as two epoxides, or they can be different, such as in chloroacetaldehyd. So chloroacetaldehyd is actually an example in this OECD guidance document. So the ideal distance between the groups appears to be in the range of 1 to 6 carbon atoms to allow the formation of DNA cyclic adducts, which tend to be more persistent. Next slide, please. So this figure lists the oncologic and genotoxicity results for 1,1-dichloroethane and 1,2-dichloroethane. Oncologic rates 1,1-dichloroethane with a low to medium concern for cancer and 1,2-dichloroethane with an overlapping medium concern for cancer. So 1,1-dichloroethane structurally is a geminal alkyl dihalide, which is less chemically reactive than 1,2-dichloroethane, which is a vicinal alkyl dihalide. So both chemicals are positive in the Ames assay with and without metabolic activation, and that's a very important point. DNA also positive in the DNA repair test in both rats and mice. They produced endometrial polyp precursors, and they're both directly chemically reactive without metabolic activation. Next slide, please. So in summary, this figure lists the key points and to support read across from 1,2-dichloroethane data to 1,1-dichloroethane. 1,2-dichloroethane was identified as the best available candidate chemical to fill the identified data gaps for 1,1-dichloroethane on a weight of scientific evidence approach. This conclusion is based on both 1,1 and 1,2-dichloroethane are structurally similar as reactive dichlorinated ethanes. They both have there's good similarity indices of 0.63 to 0.79. Both are isomers of each other with identical molecular weights and formulas. Both have similar physical chemical properties. Both are volatile liquids. Both have similar ADME patterns qualitatively and metabolic pathways to produce reactive species to produce hazards. Both are reactive alkyl halides without metabolic activation, and both possess overall similar non-cancer and cancer hazards, available mutagenicity, common tumor types, and many common hazard endpoints, for example. EPA is the highest confidence using 1,2-dichloroethane as an analog for 1,1-dichloroethane for human health. And thank you for your attention.
Thank you. And now we can look to the committee for questions related to the presentation. I see Dr. Stice.
Yes, thank you for the presentation. I have two questions. The first question is, could you clarify what the difference is between first pass and second pass analogs in AIM?
Sure. So this is in the analog identification methodology, which we used in new chemicals frequently. It's where the program is set up. If you know how it works, it chops up the molecule into fragments and then searches for the most similar. So it does a first pass, and then you can actually have it do more passes than that to get analogs that have less structural similarity. And there's various rules in that. I don't know exactly what the thresholds are, but they do divide it up into close analogs and then ones that are not as close.
I think that would have been nice to include in your documents. And thank you for the clarification. I have one more question. You identified early on more than one analog, and you quickly dismissed those. Have you compared the metabolic and toxicological similarity of those analogs to your substance of interest? And if you did so, is it possible to have that data so we ourselves can determine whether you indeed chose the best analog for your substance?
Well, we did look at the toxicology for the other ones. It was clear that 1,2-dichloroethane had the most robust database for endpoint selection and POD selection. In particular, the 1,2-dichloroethane had an excellent inhalation cancer study that was very prominent. Put a lot of weight on selecting it. That's why early in the presentation I underlined available data, because 1,2-dichloroethane by far had the most available data to fill in the data gaps.
So, but that for me also means that it may not be actually the best analog, but one of the main reasons you chose it is because it's very data rich. That said, I think it would have been very nice to see the toxicological and metabolic similarities of the other analogs to your compound of interest. And just one more follow-up question. Have you thought about doing a category approach over an analog approach? And if not, could you explain us why you chose an analog approach?
Well, yes. So TSCA does have the chemical categories. There's 56 of them for fairly well-defined chemicals like isocyanates and so on, where there is a category type approach. We really we don't have a category developed for these chemicals for human health.
Thank you. So thank you for the questions and the response. Dr. Fong.
Yeah, thank you very much. And thanks for the presentation, Dr. Irwin. Actually, I'm just looking for clarification on slide 51. What was the point that you made about reducing glutathione levels and tumorigenicity? I completely missed it on slide 51. So I'm sorry, what's the decrease in glutathione levels? Are you using that as an indicator for reactive, chemical species? Or I'm reading through the document and looking at this, I guess I just completely missed the point.
Well, the EPA has regulated chemicals on decreases in glutathione levels for the exact reason that you've mentioned. When glutathione levels are decreased, there's a tendency for reactive oxygen species to be increased. And you need glutathione for important metabolic pathways, especially for detoxification and conjugation. So decreasing glutathione is an important consideration in the hazards.
Okay, great. Thank you very much.
All right, Dr. Fox.
Hi, yeah, so my question, I think, is for Janet Burris or others on the team regarding the systematic review. So the presentation gave a good job of sort of the data evaluation pieces of the review, but it might be helpful also to have on the record for the meeting, actually sort of a couple steps back from that. What are the data sources or databases that get searched?
I think we're waiting on people to change places.
Yeah. Yes, this is William Irwin. We're conferring on answering your question at the moment.
Okay, that information is in one of the supplemental files associated with the systematic review process. And it lists the databases that were searched, and I think it has even the search strings in it. I don't have the document in front of me to point directly to that, but it is in one of the supplemental files associated with the systematic review.
So yeah, perhaps if someone, it doesn't have to be right now, just at a break or even tomorrow, lets us know which document and where. I think that would maybe self-explanatory once the specific document is cited, and there's just so many in the docket, sometimes it's hard to find them. But thanks for that response. Mary, does that answer your question, Dr. Fox?
Yeah, I'm good. It would be very helpful to pinpoint the document, though. I would appreciate that. Yeah.
Yes.
I understand. Will do.
All right. Next up is Dr. Rose.
Yeah. Oh boy. Oh gosh. My camera says it's on, but it looks like it's black. I apologize. I'll work on that in the break. But thank you, Dr. Irwin, for the presentation. My question relates to the comment that you made around evaluation of the toxicity data for 1,1 and 1,2 dichloroethane. And you said that you did a qualitative evaluation of the data and that separately you did a dose response analysis of the data for the two chemicals, and that you saw differences in those chemicals, but number one, I guess I didn't see that evaluation completed and written up in the document. And if it is available, that quantitative evaluation of the two target and analog chemicals, it would be helpful to see that evaluation.
Anything from EPA on that?
And maybe one additional comment to that. I mean, certainly the 1,1 dichloroethane data might not rise to the level of being able to derive points of departure for risk evaluation, but could potentially be used in a weight of evidence to support the analog comparison to the target chemical.
Yes, thank you, Dr. Graham. This is Catherine Anatole. I'm one of the human health assessors for the draft risk evaluation. That information on either the quantitative or qualitative aspects of the human health data for 1,1-dichloroethane are in the body of the RE. And the issue is that we have very little data to do quantitative dose response for 1,1-DCA. But that analysis for the data that we do have is in the body of the RE. To this particular, we can get that particular section for you later.
Okay, thank you.
Yes, if we can get those specific sections, that would be helpful. Dr. Graham.
Hi, this is kind of a follow-up to Mary Fox's question. The review said that there's a full text screen, and I'm curious as to what that exactly means. Are you using like a mechanical AI, control find for certain words? Or are you actually reading through these articles as a initial screen?
That's an excellent question.
Okay, well, thank you. That's an excellent question. Unfortunately, we do not have the personnel in the room that completed that portion. It's actually done in a separate division. So we will be getting back to you with the answer to that question.
Thank you very much.
So, thanks for the question and for the answer. I will say, Dr. Graham, that when we did a systematic review meeting a year or more ago, one of the things was that a lot of the screening was done with electronic means, and then some things were verified by humans, and I do not remember where that cutoff was, frankly. But that should be something that the agency can let us know relatively quickly.
I just know that in various articles, people will say things differently and use various words that you may not be looking for. So that's why I posed that question.
Yes, exactly. And there are a lot of reasons that you can miss things with, even when you're trying to scour words that people are using. Sometimes it does not quite give you everything that you're looking for. Okay. Other questions? All right. Since we have none, we can move on to our next presentation. That's going to be on the non-cancer oral human health assessments. And Dr. Shohati.
Thank you, Dr. Cobb. Good afternoon, everyone. My name is Ali Shohati, and I am a human health assessor from EPA's Office of Pollution Prevention and Toxics. And I'll be presenting on the 1,1 and 1,2 dichloroethane draft non-cancer oral human health hazard assessment. Next slide, please. So as mentioned earlier, existing assessments, as well as the studies identified in those assessments, are integrated within the data evaluation and extraction phases of the systematic review process to identify candidate points of departure to be used in EPA's risk evaluations. One example of this is EPA's PPR-TV 2006 assessment for 1,1 dichloroethane. With regard to this assessment, the PPR-TV assessment for subchronic duration identified a study by Moldahara et al. 2001, which identified the kidney as a sensitive target for 1,1 dichloroethane in male rats. A NOEL and LOEL value values of 1,000, 2,000 mg per kg per day were identified and estimated based on increased urinary enzyme markers for renal damage and CNS depression. NOEL of 1,000 milligrams per kilogram per day administered for 5 days a week was then adjusted to 7.4.3 milligrams per kilogram per day for continuous exposure. The equation below identifies how this value was these values were utilized to calculate subchronic provisional reference dose of 2.4 milligrams per kilogram per day. The table below summarizes US EPA's provisional peer review file value, or PPRTV, for 1,1-dichloroethane in this 2006 assessment, as well as it outlines the uncertainty factors that were applied to this POD in this document. Next slide, please. So the existing assessment and PPRTV 2006 also identified a chronic oral duration provisional reference dose. The subchronic oral exposure study by Moll-Dahar et al. 2001 was also used for the chronic duration, and such that the NOEL of the 1,000 again adjusted to 714.3 milligrams per kilogram per day for continuous exposure was used. And the table below summarizes how EPA applied particular uncertainty factors to this POD to identify this chronic provisional reference dose. Next slide, please. An additional assessment that was evaluated by EPA in preparation for the 1,1-dichloroethane risk evaluation was the ATSDR 2015 toxicological profile for 1,1-dichloroethane. In this document, oral minimal risk levels or limits or MRLs was not identified for 1,1-dichloroethane, as the database, as per ATSDR's indication, was considered inadequate. Next slide, please. So as mentioned previously, as part of the systematic review process regarding 1,1-dichloroethane, no adequate data for non-cancer oral hazard were identified. Now, although the Moll-Dahar 2001 study, which was the basis for deriving EPA's PPRTV subchronic chronic provisional reference doses, was identified, it was, however, not selected for dose response, even though it was rated high by our office's systematic review. The key characteristics of the study that resulted in non-selection was that the NOEL was near the limit dose of 1,000 milligrams per kilogram per day, only in male rats. Histological effects on the kidney showed nephropathy with high incidences in the control group as well, in 7 of the 10 animals. Mortality in the highest 2 groups of 2,000 and 4,000 milligrams per kilogram body weight per day in the study also result in a ceasing and the continuation of exposure at these highest doses. In addition, the methodology for CNS depression was not defined, and results were also only described qualitatively. Thus, for this evaluation, this study was not used as a candidate POD. No available data for the dermal hazard for all exposure durations, which include the acute, short-term, and chronic, were identified. And sections 5.2.3.1 in the 1,1-dichloroethane draft evaluation outlines the hazard identification evidence integration associated with 1,2, as well as 1,1 and 1,2-dichloroethane exposure by health outcome. The data caps filled by read across from the identified human health hazard of the chemical analog 1,2 was then applied. Next slide, please. So with regards to the 1,1-dichloroethane non-cancer acute oral duration point of departure, non-cancer POD was based on a benchmark response of 10% of a 153 milligram per kilogram per day to 1,2-dichloroethane based on increased kidney weight in male mice. Allometric body weight scaling to the 3/4 power was used to derive the human equivalent dose of 19.9 milligrams per kilogram per day for this benchmark dose level of 10. A total uncertainty factor of 30 was proposed as the benchmark margin of exposure, and this is based on a composite of an interspecies uncertainty factor of 10, an interspecies uncertainty factor of 3, which was reduced from 10, and is consistent with US EPA's guidance from 2011. As indicated earlier, no a suitable dermal study relevant for dose response was identified, and thus a route-to-route extrapolation from the oral POD or the corresponding dermal POD was used. The table below, which is adapted from table 5-49 from the 1-1 draft risk evaluation, summarizes the POD as well as the uncertainty factors applied for this value. Next slide, please. So with regard to the weight of scientific evidence in support of the non-cancer acute oral POD, as indicated earlier, adequate data was not available to identify PODs following acute oral exposure to 1,1-dichloroethane, and thus the read-across approach from 1,2-dichloroethane was required to fill in this data gap. Increased kidney weights in Store et al. 1984 was selected as the critical endpoint from among several acute toxicity studies. And it's important to note that increased L-idiol dehydrogenase and blood urea nitrogen were considered as co-critical endpoints in the same study. Now, other studies, such as study by Morel et al. 1999, which identified damaged renal tubules, was considered. However, due to uncertainties due to dose groups, due to the dose groups being above the limit dose, reduced EPA's confidence for its use in the risk assessment to derive PODs. Acute oral studies and those PODs for both 1,1-dichloroethane and 1,2-dichloroethane toxicity data used in support of the critical and co-critical endpoints are presented in table 5-42 in the 1,1-dichloroethane draft risk evaluation. Next slide, please. With regard to the 1,1-dichloroethane non-cancer subchronic oral duration point of departure, a non-cancer POD based on the low L of 4.89 milligrams per kilogram per day to 1,2-dichloroethane, which is based on the identification of suppression of the immune system, specifically antibody-presenting cells in the spleen in male mice. Allometric body weight scaling to the 3/4 power again was used to derive both a worker and general population human equivalent dose of 0.890 and 0.636 milligrams per kilogram per day, respectively. A total uncertainty factor of 100 was proposed as the benchmark margin of exposure, which is a composite based on an intraspecies uncertainty factor of 10, an interspecies uncertainty factor of 3, and a low L to no L uncertainty factor of 3 to account for uncertainty inherent in extrapolating from the low L to no L. And these are consistent with US EPA's guidance 2011. Again, with regard to the data, subchronic, no suitable dermal data was available for the subchronic duration, and thus a route-to-route extrapolation from the oral to dermal POD was then used again. The table below is adapted from table 5-50 within the 1,1-dichloroethane draft risk evaluation, which summarizes the POD selected as well as the uncertainty factors that were applied for this particular duration. Next slide, please. With regard to the 1,1-dichloroethane non-cancer chronic oral duration point of departure, the Munson et al. 1982 study identified for the subchronic oral non-cancer was used for the chronic oral duration as well. A total uncertainty factor of 1,000 was proposed as the benchmark margin of exposure. And this is a composite uncertainty factor based on an intraspecies uncertainty factor of 10, an interspecies uncertainty factor of 3, a low L to no L uncertainty factor of 3x to account for uncertainty inherent in extrapolating from a low L to no L, and a subchronic to chronic duration uncertainty factor which are all consistent with US EPA guidance from 2011. Again, due to limited data, chronic dermal study was not found, or there were no suitable dermal studies for this duration, and thus, again, a route-to-route extrapolation from the oral to dermal was applied. The summary below, the table below summarizes and is adapted from table 5-51 in the 1,1 dichloroethane draft risk evaluation, which outlines the POD of low L of 4.89 milligrams per kg per day, and outlines the uncertainty factors that were applied to this POD for this duration. Next slide, please. So with regard to the weight of evidence in support of the non-cancer subchronic and chronic oral PODs, the low L of 4.89, again, based on a suppression of immune response in Munson et al. 1982, is supported by other findings, specifically a decrease in leukocytes, which was considered as a co-critical effect and identified in the same Munson et al. 1982 study. Within our evaluation, we do want to acknowledge with ATSDR's draft as well as subsequent final toxicological profile for 1,2 dichloroethane that concluded that the immune system was the most sensitive target for short-term exposure to 1,2 dichloroethane by both inhalation and oral routes in mice. It is important to note that the 14-day Munson et al. 1982 gavage study was considered as an acute duration by ATSDR, thus not utilized for the subchronic or chronic PODs in the ATSDR assessment. It is also important to note that acute studies, as per ATSDR, are defined as those studies that are less than 15 days in duration. Additionally, recommended subchronic and chronic oral studies and PODs for both 1,1 dichloroethane and 1,2 dichloroethane toxicity data, as well as co-critical endpoints in support of this recommended POD, are presented in tables 5-44 and 5-46 in the 1,1 dichloroethane draft risk evaluation. Next slide, please. Okay, with regard to this, we kind of wanted this slide. Basically, we want to go through how, as mentioned earlier, that existence assessments as well as the studies identified in those are integrated within the data evaluation extraction phases of the systematic review. And with regard to the EPA's PPR-TV 2010 assessment for 1,2 dichloroethane, this assessment identified a subchronic duration based on a 13-week study by NTP 1991 in male and female F344N rats exposed to 1,2 dichloroethane in drinking water, and was used to derive the subchronic provisional reference dose in this assessment. The endpoint identified was a significant dose-related increase in kidney weight and the kidney body rate, and an increase in the kidney body ratio in female rats at 58 milligrams per kilogram per day. The equation below is how the subchronic provisional reference dose was calculated in this assessment, and the table below summarizes US EPA's provisional peer review toxicity value for 1,2 dichloroethane in this assessment, and includes the POD as well as the uncertainty factors applied in this assessment. Next slide, please. With regard to the PPR-TV 2010 assessment for 1,2 dichloroethane for the chronic duration, this assessment outlines that due to the absence of suitable chronic data, the POD from the subchronic provisional reference dose could have been used to derive the chronic provisional reference dose. However, the composite uncertainty factor would include the additional uncertainty factor for the subchronic to chronic duration of 10 for applying data. This would then ultimately result in a large composite uncertainty factor greater than 3,000, which thereby relegated its derivation for the chronic provisional reference dose to an appendix screening value. The equation below outlines this calculation of how the screening chronic provisional reference dose was calculated, and the table below summarizes this value within this respective risk evaluation, as well as the uncertainty factors applied in this assessment. Next slide, please. So in addition to evaluating PPR-TV's assessment of these chemicals, ATSTR's 2022 draft toxicology profile for 1,2-dichloroethane was also evaluated. Within this document, an intermediate duration was based on the same 13-week study by NTP 1991, as was the case in PPR-TV's assessment, where rats again are exposed to 1,2-dichloroethane in drinking water, and was used to derive the intermediate duration oral minimal risk level for this assessment. The endpoint identified is based on increased kidney weight in female F3, 4, and rats. The equation below identifies how the intermediate duration oral MRL was calculated, and the table below summarizes this POD as well as the uncertainty factors applied within this assessment. Next slide, please. As indicated earlier, the ATSTR toxicological profile for 1,2-dichloroethane was final version was recently released in July of 2024. And the intermediate duration is, although still based on the 13-week study by NTP 1981 with rats exposed to 1,2-dichloroethane in drinking water, the endpoint identified is now based on increased incidence of kidney lesions, which are accompanied by tubular regeneration in female F3, 4, and rats. The equation below indicates how the intermediate duration oral MRL was calculated. And it is important to note that this is based now on a benchmark dose level of 10. And the table below summarizes this POD and this updated toxicological profile for 1,2-dichloroethane, as well as the uncertainty factors that are applied for this POD and within this assessment. Next slide, please. Now, regarding the ATSTR 2022 draft, as well as the final 2024 toxicological profile for 1,2-dichloroethane, the chronic duration in both of these documents remain as that they both indicate that the available data are insufficient for derivation of a chronic duration oral MRL for 1,2-dichloroethane, and thus a chronic duration POD was not included in that assessment. Next slide, please. So EPA is now soliciting comment on the rationale for not selecting the NTP 1991 drinking water study for the subchronic and chronic oral PODs. OPPT systematic review rating of was deemed the study as uninformative for dose response. This NTP 99 study was reviewed for POD derivation. However, the daily intake doses were estimated on a milligram per kilogram body weight basis and not measured throughout the duration of the exposure, putting uncertainty in the doses. It is also important to note that the water consumption was not corrected for spillage, as indicated in the study report. Weight gain depression seen in male and female rats in the two higher dose groups throughout the study was seen, and likely was attributed to dehydration due to poor palatability or of the formulated drinking water. The study also indicated water consumption was substantially decreased with increased dose, and analysis of formulations within the drinking water bottles after 24 hours in the animal cages showed that the concentrations of the formulation had decreased an average of 29%, ranging from 13 to 53% of target concentrations. Due to the uncertainty regarding the delivered dose and the inherent volatility associated with 1,2-dichloroethane, it was not recommended using this drinking water study for this dose response assessment. Next slide, please. So EPA's PPR-TV for 1,2-dichloroethane also identified the Munson et al. 1982 study, specifically the 90-day drinking water portion of this study, where male and female CD1 mice were exposed to 1,2-dichloroethane, and suggested that the NOEL of the study would be the highest dose tested of 189 milligrams per kilogram per day. The subchronic reference dose for the oral reference dose was ultimately based, however, on the 13-week study by NTP 1991. The ATSDR 2022 draft toxicological profile for 1,2-dichloroethane identified the same NTP 1991 drinking water study for the intermediate duration oral MRL of 58 milligrams per kilogram per day, a NOEL value, based on increased absolute kidney weights in the female F344N rats exposed to 1,2-dichloroethane with an uncertainty factor of 300. Now, again, just to reiterate here, the immune system was identified as the most sensitive target for short-term exposure to 1,2-dichloroethane by both inhalation and oral routes in mice. However, ATSDR concluded that the data provided limited evidence that the immune system is a sensitive target for 1,2-dichloroethane in mice, but not rats. ATSDR also identifies that due to apparent interspecies differences in animal immunotoxicity, it is unclear whether the immune system could be a target for 1,2-dichloroethane in humans following exposure by inhalation or ingestion. Additionally, ATSDR identifies that the mechanism by which 1,2-dichloroethane producing these immunological effects is not known. The final ATSDR 2024 toxicological profile for 1,2-dichloroethane has now identified increased kidney lesions associated with tubular regeneration as a basis for their intermediate duration MRL. Next slide, please. So a summary of the studies not considered or considered suitable for PODs and dose response assessment for the 1,1-dichloroethane and 1,2-dichloroethane can be found in sections M.2.1 and M.2.2 in the 1,1-dichloroethane draft risk evaluation respectively. And evaluation results for studies identified from the 1,1 and 1,2-dichloroethane databases can be found in the 1,1-dichloroethane draft data quality evaluation information for human health hazard animal toxicology supplemental file. And EPA has provided conclusions that are summarized in sections 5.2.6.4 of the 1,1-dichloroethane draft risk evaluation. Next slide, please. EPA is also soliciting comments on rationale for not selecting the OECD guideline 443 study for dose response. So just to provide some background, in 2015, OPPT received the OECD guideline 443 study entitled An Extended One-Generational Drinking Water Reproductive Toxicity Study for Ethylene Dichloride, which is synonym of 1,2-dichloroethane in rats from Will Research Laboratories in 2015. This study was conducted to fulfill one of the requirements of an enforceable consent agreement under Section 4 of TSCA. And during the agency review of the data protocol for this study, the agency identified palatability and volatility as possible issues to be addressed. And after consideration of the response from the HAP task force, approved the protocol in November of 2011. Next slide, please. In preparation of the 1,1-dichloroethane draft risk evaluation, OPPT systematic review identified the study as uninformative for dose response. This study was reviewed for POD derivation. However, it was identified by the study authors that concentration-dependent reductions in water intake throughout the study period was likely due to issues with palatability. In addition, water intake was reduced by 20% in the mid and high dose groups, and there were corresponding reductions in body weights. The authors note also that many of the effects observed, such as decreased body weights and organ weights, stem from reduced water intake and likely due to dehydration. Due to the uncertainty regarding the delivered dose as exposure levels were below the target and the effects observed, systematic review recommended not using this drinking water study for this dose response assessment. Additional details regarding the study quality evaluation are available on pages 919 through 938 in the 1,1-dichloroethane draft data quality evaluation information for human health hazard animal toxicity supplemental file. Next slide, please. And with that, I'd like to thank you all for your attention.
Thank you. So are there questions from the committee? I see Dr. Landis.
Thanks a lot. That was a very interesting summary. Wow. I'm actually I'm reviewing the Storer paper and the Munson paper. I have specific questions as to those, as to the data evaluation and so forth and so on, and what the BMDL is meaning in those particular studies. I reviewed both of those papers, and in my comments I've already sent to the committee, First, I have a caveat that this is the early 1980s when these studies were done. And our ability to look at data and the way we can design experiments is very different. I'm also very familiar with doing the BMDLs from dose response curves, which was not done in these studies. In looking at both papers, I could not see any information that would give me any indication of statistical power of the analyses that they were doing. It's not always clear to me what the replication was in each one of these, so forth and so on. So I'm wondering, and what tool did you use to calculate the BMD or BMDL? Was that looking at the low L or no L? Or was it taking data that you may have somewhere that will and do the curve fitting? And is there an evaluation by someone who is familiar with the statistics involved in this to actually try to derive statistical power or evaluate the analysis of these particular papers? I'd like to know some of that background. I know not everyone is familiar with it, but I found when I evaluate things for dose response that often these kinds of details are left out. And number one, could they be available? Number two, is anyone evaluating those aspects in those papers?
Thank you for the question. With regard to the benchmark dose modeling, we're using the BMDS tool from EPA. And the version we have indicated in our methods regarding for the benchmark dose modeling supplemental file that kind of provides the details as well as what concentrations were utilized, as well as any adjustments that were necessary when actually performing the modeling.
Right.
So I could direct you to that document at least that provides greater detail and clarity in terms of the methods and the and the data.
Yeah, I know that method fairly well, especially I focus on the dose response. I don't see how you could get dose response curves from the information in these papers that I can extract from these papers. So do you have other information that you're using to derive that? And of course, I'm focusing on an exposure response because, yeah, there's a very specific kind of tool that gets right at dose response curves.
So I can confer with the other human health assessors regarding the modeling and just to make sure that we're providing an accurate response and representation of how the data was actually in statistical power. And we can provide that follow-up as it is appropriate for the charge question that we'll be presenting later on during the SACC presentation.
That would be very helpful because I often know you have access to data, the actual raw data. Like at Duluth, if you need on their classic experiments, you can get all that information. So you may have that, and I do not. Also, when you're using a no-L or low-L, what ends your evaluations? How are you evaluating those numbers in these papers? I've already told you what's in my comments now from my reviews, but who is evaluating the experimental design and so forth to know that those are strong experimental designs for the degree of certainty that you want in your notes? And the reason I'm asking that is that we just went through a study, the NTP study, that's not included in the evaluation because it had some physiological and experimental design issues.
So with regard to any studies that are considered as part of weight of evidence, as well as any dose response, those studies are all going through systematic review. And within the systematic review process, there are various metrics that look at key elements within the study based on, if there's confounding variables, if, animals, the number of animals in the study, accuracy in the actual doses or exposures that are provided. And that systematic review process goes through several metrics to kind of address those issues. And based on how well the study is executed and how those details are provided during the review process, will determine whether a study is a potential candidate for POD derivation. So it really relies a lot on the systematic review and the metrics that are the underpinning of that method.
Can you send us a reference for that systematic review process? And I'm going to be focusing on statistical aspects and statistical design of these studies. Things have changed a lot since the mid 1980s and how we can look at data and so forth. So some of my comments may not be particularly valid if someone else has undergone that review and had access to other information I did not. So that would be, to me, an important clarification. Thank you.
Sure, and we can confer and find try to direct you to the specific documents as well as the sections in those documents that can direct you to provide clarity on that issue.
Yeah, great. Thank you very much.
So this is George Cobb. Just as part of that, perhaps our DFO Ali Munir could provide a link to the systematic review documents that we did for the SACC a few meetings ago, and that might help you, Wayne, but it might not answer the specific question for this specific analysis, but it gives you a framework.
So, George, that is exactly would be very useful. And of course, what I'm trying to do is combine how we look at this now with our current tools compared to taking things from when we were younger. and the statistical tools, just you couldn't compute these things very easily at that time. So thank you. Thanks.
All right, I see Dr. Graham has her hand up.
Yes, thank you. And thank you for the presentation. My question is on, you derived RFDs for 1,2-dichloroethane, but as it was stated previously, you know that 1,1-dichloroethane is less potent or less toxic. So how are you taking that knowledge into consideration in deriving numbers for 1,1-dichloroethane?
Thank you for a question. So with regard to within the presentation, we wanted to provide that as part of our systematic review process, it's crucial to review existing documentation. So EPA's PPRT value is derived from the Office of Research and Development. So it's a different office that has different methodology implemented. So because we had existing assessments, it's necessary to look at all available data and any studies that were identified. So with regard to looking at, because we had data gaps with regard to 1.1 and identifying read across as an approach to kind of fill in data gaps, we'll kind of get in this a little bit later in the presentation. We are trying to, the objective of this is to be human health protective, and as you'll see in the subsequent presentation, it'll provide a little bit more clarity on that front.
Yeah, but whenever you're making these assumptions, you can be actually too conservative, and you build conservative upon conservative. And I was just wondering if you take that into consideration.
And yes, I mean, in an ideal world, we'd have enough data to calculate a relative potency factor like we do on other chemicals that are data rich, like in the pesticide office. The paradox is we didn't have enough data for 1,1-dichloroethane, period. We really only had one good study that had a high systematic review rating that was the Merle-Hara study, and it was only in male rats, and it was just a generic tox study. So really, we couldn't calculate a relative potency factor between the two chemicals. So we're doing a direct read across in the absence of doing any kind of analysis such as that. So
In the previous, it was Janet Burris showed how she was doing read across, and it showed that these other potential analogs were all more toxic, so more protective than 1,1. So in a way that shows potency, it may not be a quantitative potency, but it does show that 1,1 is less potent than those others. So, you know, you're taking that into consideration to use an analog, but you're not taking that into consideration to develop RFDs or numbers or PODs or anything like that?
I mean, we can follow up when we do the charge questions. I mean, if you're talking about ecotoxicology, they have different models in human health, for example. So kind of apples and oranges comparison, but we can follow up later on the charge questions on this topic.
I think that would need to be clarified as to whether the relative potencies were considered in the computation during the read across. And yes, we can certainly get to that when we get to the charge question itself, if that is okay with you, Dr. Graham.
Yes, thank you.
Okay. Any other questions from the committee? All right. So our next presentation is on the non-cancer inhalation human health assessments, and that's going to be Dr. Anatoly.
Can get it to unmute.
Okay, thank you. Good afternoon to the Scientific Advisory Committee on Chemicals, public commenters, and stakeholders. My name is Catherine Anatole, and I'm one of the human health assessors on the 1,1-dichloroethane risk evaluation team. I will be going over the next series of slides describing EPA's assessment of the 1,1-dichloroethane data for dose response analysis for identification of non-cancer points of departure by the inhalation route, as well as EPA's cancer assessment. Next slide, please. This slide summarizes the non-cancer point of departure EPA identified for human health hazard for the inhalation route for the acute exposure duration for 1,1-dichloroethane. But first, let me start off by saying that in summary, as we have been discussing, EPA did not identify points of departure for 1,1-dichloroethane for the acute, short-term, subchronic, or chronic inhalation exposure durations that could be used for the draft risk evaluation. As a result, a read-across approach was employed by using data from its close structural analog, 1,2-dichloroethane, to fill in those data gaps. This was described earlier in this presentation. For 1,1-dichloroethane for the acute duration, there were no inhalation exposure studies of less than or equal to 24 hours identified. The only study available by the inhalation route was a single prenatal developmental toxicity study in rats by Schwetz et al. In 1974. However, this study was not considered for the identification of a point of departure for the acute exposure scenario because there were no signs of developmental toxicity. Only adult maternal toxicity was reported, consisting of changes in body weight gain. However, use of an adult endpoint for an acute exposure scenario following repeated exposures is not considered appropriate. Therefore, data for 1,2-dichloroethane was used as read across for this scenario. In a weight of evidence integration and evaluation of the database for 1,2-dichloroethane, an 8-hour inhalation toxicity study by Dow Chemical in 2006 was selected for the acute exposure scenario. This study showed a degeneration and necrosis of the olfactory neuroepithelial mucosa at a NOAC of 202 milligrams per meter cubed, or 71.3 milligrams per meter cubed for an adjusted continuous exposure concentration, with a BMCL10 of 48.9 milligrams per meter cubed. This endpoint was selected as the critical endpoint from among several acute toxicity studies. ATSDR in 2022 and 2024 also selected this endpoint for this same scenario. This will be discussed in subsequent slides. When allometric body weight scaling to the 3/4 power was used, a human equivalent concentration, or HEC, of 41.1 milligram per cubic meter for worker exposures and 9.78 milligrams per meter cubed for continuous exposures from the BMCL10 was derived. A benchmark MOE of 30 was based with a combination of uncertainty factors that included an intraspecies uncertainty factor of 10x and an interspecies uncertainty factor of 3x. And as a point of reference, the information on this slide is adapted from table 5-49 in the draft risk evaluation. Next slide, please. So in summary, since adequate data for points of departure are not available for acute inhalation exposures to 1,1-dichloroethane, a read across from 1,2-dichloroethane was used. Degeneration and necrosis of the olfactory neuroepithelial mucosa from the Dow 2006 study was selected as the critical endpoint from among several acute toxicity studies. A co-critical endpoint of decreased body weight was also identified in Rayo et al. 1980. I should note that the Rayo study used for co-critical endpoints had a BMCL10 very close to that from the recommended critical endpoint, 50 versus 48.9 milligrams per meter cube. However, when a NOEC low-EC basis is considered, the critical endpoint will be protective of the decreases in body weight. And again, as a point of reference, this information can be found in the draft RE. It's noted at the bottom of the slide. Next slide, please. As mentioned, the ATSDR toxicological profile for 1,2-dichloroethane used the same inhalation point of departure for the acute duration exposure in their 2022 draft and 2024 final toxicological profile for 1,2-dichloroethane as EPA is using. As you can see on this slide, if we compare calculated RFC values between EPA and the minimum risk levels, or MRLs, in the 2022 draft ATSDR profile, there is very close similarity, 1.37 versus 1.2 milligrams per cubic meter. However, in the final 2024 ATSDR, although the same point of departure is used from the same study, differences in the methods and the models used generated a different MRL. The differences in the draft 2022 and final 2024 ATSDR calculations will be described later in this presentation. Next slide, please. Benchmark dose modeling was completed and used for several non-cancer points of departure for acute inhalation, including degeneration with necrosis of the olfactory neuroepithelial mucosa, the selected critical endpoint, which had a NOEC of 71.3 milligrams per meter cubed for an adjusted continuous exposure concentration, and with a BMCL10 of 48.9 milligrams per meter cube, all from the Dow Chemical Study 2006. The modeling results are shown on the next slide. A benchmark response level of 10% was chosen according to EPA's BMD technical guidance in 2012. And again, this information can be found in the supplemental file on benchmark dose modeling that accompanies the draft risk evaluation. Next slide, please. This slide shows the BMD modeling results for increased incidence of degeneration with necrosis of the olfactory mucosa in male rats. All models provided adequate fit to the data, except for the multi-stage 1-degree quantilinear model. The BMDLs of the fit models were sufficiently close, differing by less than 3-fold. Therefore, EPA chose a model with the lowest AIC, and that was the multi-stage 3-degree model. Again, this information can be found in the benchmark dose modeling supplemental file. Next slide, please. This slide shows the plot of the multi-stage 3-degree model with a BMR of 10% extra risk for the critical non-cancer endpoint from the Dow study. As can be seen on this graph, the BMDL is less than threefold below the adjusted NOAC of 71.3 milligrams per cubic meter from that study. Next slide, please. And again, as can be seen from the graph on the previous slide, the statistical lower confidence limit, or BMCL, on the concentration at the BMC used as a non-cancer inhalation point of departure for the acute exposure duration is lower than the NOAC. The US EPA benchmark dose technical guidance from 2012 states that extrapolation sufficiently below the observable range may be too uncertain to reliably estimate BMDs and BMDLs for the selected BMR. For example, when all the dose groups have near maximal responses. The guidance further states that in such cases, BMD modeling is not recommended, and obtaining more data or using the no-AL, low-AL approach, while recognizing the inabilities of that approach to resolve the data limitations, may be warranted. However, in this case, the BMCL of the fit models for the critical endpoint from the Dow study was sufficiently close. BMCL of 48.9 milligrams per meter cube is less than threefold below the adjusted NOAC of 71.3 milligrams per meter cube. And although the benchmark model data from the 2006 Dow chemical study was lower than the NOAC, the BMCL can be less than the lowest dose and can be less than the NOAC value. And this is because, according to benchmark dose training by EPA in 2024, the NOAC approach can inappropriately reward underpowered studies. And the link to that training is on the bottom of this slide. So ultimately, we are therefore soliciting comments on the benchmark response levels selected, the benchmark dose analyses used, and the clarity and completeness of the description of the BMC analysis as they are described and presented in the draft risk evaluation, including the supplemental file on benchmark dose modeling that accompanies the draft risk evaluation. Next slide, please. The only study available in the 1,1-dichloroethane database to evaluate toxicity following short-term subchronic exposures by the inhalation route was a 1974 study by Schwetz et al., where decreased maternal body weight was seen close to 4,000 parts per million. However, there were several limitations in the study that precluded its use for POD derivation. These limitations are described in more detail in section 5.2.6.1.3 of the draft risk evaluation. And again, like with the acute inhalation exposure scenario, there were no studies in the 1,1-dichloroethane database that measured comprehensive endpoints for subchronic exposures. So as a result, read across from 1,2-dichloroethane was used to fill in this data gap. After a full evaluation of the 1,2-dichloroethane database, a 4-week short-term study in male mice exposed to 1,2-dichloroethane by Zhang et al. In 2017 was used as a point of departure. This point of departure was based on decreases in sperm concentration in male mice with a benchmark response of 5% of 21.2 milligrams per meter cube. When allometric body weight scaling to the 3/4 power was used, a human equivalency concentration of 89.0 milligrams per meter cube for worker exposures and 20.2 milligrams per cubic meter for continuous exposures from the BMCL5 was derived. A benchmark MOE of 30 was based on a combination of uncertainty factors that included an interspecies uncertainty factor of 10x and an interspecies uncertainty factor of 3x. And again, this information is adapted from table 5-50 in the draft risk evaluation. Next slide, please. So again, adequate data is not available to identify points of departure following subchronic inhalation exposures to 1,1-dichloroethane. Read across from 1,2-dichloroethane was required to fill in this data gap. Decreases in sperm concentration was selected as the critical endpoint from among several subchronic toxicity studies. The co-critical endpoint of decrease in pup body weight with a BMCL of 25 mg per cubic meter was also identified. The critical endpoint will be human health protective of the decreases in body weight. Benchmark response of 5% was conducted because EPA considers a greater than 5% change in sperm concentration to be biologically relevant. The BMCL5 of 21.2 milligrams per cubic meter is less than threefold below the lowest concentration tested of 25.68 milligrams per cubic meter, and therefore is considered a reliable extrapolation according to BMD guidance. And again, the information in the draft RE is located at the bottom of the screen where additional details are provided. Next slide, please. For 1,1-dichloroethane, there were no points of departure identified from chronic studies for inhalation exposures to 1,1-dichloroethane. There were several subchronic duration inhalation studies that EPA considered in the dose response assessment for use in the risk evaluation. However, there are several limitations in these studies that precluded their use for POD derivation, and these limitations are described in more detail in section 52614 and table 547 of the draft risk evaluation. So again, we are using read across from 1,2-dichloroethane to derive a chronic inhalation point of departure. Following a review of the 1,2-dichloroethane database, the 4-week short-term study in male mice by Zhang in 2017 was considered the most sensitive and biologically relevant point of departure for read across to 1,1-dichloroethane. This is the same study used for the short-term subchronic exposure duration scenario. The same benchmark responses and allometric adjustments as with the short-term subchronic durations were used here for the chronic duration, but in this case, a benchmark MOE of 300 was derived based on an additional uncertainty factor of 10 being applied for extrapolating from a short-term subchronic to chronic study duration. And table 5-51 in the draft risk evaluation provides more details. Next slide. So in summary, adequate data are not available to identify points of departure following chronic inhalation exposures to 1,1-dichloroethane. Therefore, read across from 1,2-dichloroethane was used to fill in this data gap. Decreases in sperm concentration was selected as the critical endpoint from among several subchronic toxicity studies with decreased body weight as a co-critical endpoint. Both studies had very similar benchmark concentrations. A subchronic to chronic uncertainty factor of 10 was applied to account for uncertainty of using a short-term or subchronic study for chronic duration. I should note that there is a 104-week chronic duration inhalation study by Nagano in 2006 available for 1,2-dichloroethane. And although uncertainty regarding study duration may have been reduced, this study did not adequately evaluate non-cancer effects, thereby precluding its use. Benchmark response of 5% was conducted because EPA considers a greater than 5% change in sperm concentration to be biologically relevant, and the BMCL5 of 21.2 milligrams per meter cube is less than threefold below the lowest concentration tested in that study of 25.68 milligrams per meter cube. And again, this is adapted from table 5-47 in the draft risk evaluation. Next slide, please. The next series of slides compare the 1,2-dichloroethane non-cancer inhalation human health hazard values used by other EPA offices and agencies. So first, for 1,1-dichloroethane, as Dr. Shohati previously mentioned, the acute short-term subchronic or chronic exposure non-cancer inhalation points of departure for 1,1 and 1,2-dichloroethane were not assessed under the IRIS program. In addition, the PPR-TV assessment for 1,1-dichloroethane concluded that non-cancer inhalation toxicity data for 1,1-dichloroethane were inadequate for derivation of a provisional acute subchronic or chronic RFC value. Likewise, the ATSDR in 2015 toxicological profile for 1,1-dichloroethane concluded that the non-cancer inhalation toxicity data for 1,1-dichloroethane were not considered adequate for deriving inhalation MRLs for any duration. So now looking at what was done for 1,2-dichloroethane for the non-cancer inhalation PODs across other program offices, starting with the PPR-TV program, a provisional RFC was not derived for the acute inhalation point of departure. Animal data was not used to derive a provisional value for the subchronic inhalation point of departure, but instead a provisional value for the subchronic inhalation point of departure generated RFC of 0.07 milligrams per cubic meter, which was based on neurobehavioral impairment in a human study by Kozik in 1957, with a total combined uncertainty factor of 300. The PPRTV states that confidence in the Kozik study is very low. They applied a UFD of 3 in their total uncertainty factor calculation, and overall, their confidence in the calculation of the provisional RFC was low. This study likewise rated as uninformative in our systematic review. And this information is presented in Table 5-53 and Section 5.2.6.4 in the draft risk evaluation. Next slide, please. This slide summarizes the PPRTV provisional value for the chronic inhalation point of departure of 0.007 milligrams per cubic meter. It was based on, again, neural behavioral impairment from the Kozik study. This time they applied a total uncertainty factor of 3,000, thereby relegating this derivation of the chronic provisional RFC to an appendix screening value. And the information can be found in Table 5-53 and Section 5.2.6.4 in the draft risk evaluation. Next slide, please. So this slide summarizes the MRLs in the 2022 draft ATSDR toxicological profile for 1,2-dichloroethane. The ATSDR minimum risk level for the acute inhalation POD was 0.3 parts per million, or 1 milligram per cubic meter. Was based on degeneration with necrosis of the olfactory epithelium in rats, which is the same study that EPA used. A BMCL-10 of 57 milligrams per cubic meter and an uncertainty factor of 30 was applied. The values between ATSDR in 2022 and 1,2-dichloroethane draft risk evaluation were compared in a previous slide. ATSDR did not derive MRLs for the subchronic or chronic inhalation point of departure in 2022. Next slide, please. This slide summarizes the acute duration MRL in the final 2024 ATSDR toxicological profile for 1,2-dichloroethane. The acute duration MRL used is the same as in 2022, the Dow study. A minimum risk level for the acute inhalation POD was 0.1 parts per million, or 0.4 milligrams per cubic meter, based on degeneration with necrosis olfactory epithelium in rats, with a BMCL-10 of 233.21 milligrams per cubic meter and a BMCL-HEC of 15.54 milligrams per cubic meter, applying a total uncertainty factor of 30. The difference between ATSDR 2022 and 2024 acute duration MRL, in the ATSDR for 2022, only females were used for 4-hour exposure duration, and the BMDS modeling was version 3.1.2, whereas in 2024, male and females were combined for an 8-hour exposure duration, and the BMDS modeling was version 3.2.0.1. Next slide, please. Unlike the draft 2022 ATSDR for 1,2-dichloroethane, the 2024 ATSDR did derive an intermediate inhalation MRL. The MRL for the intermediate inhalation POD was 0.1 parts per million, or 0.4 milligrams per cubic meter, based on altered behavior in an open field test in mice in a 28-day inhalation study by Zhang et al. From 2022. The BMCL 1 standard deviation was 59.9 milligrams per cubic meter, and the BMCL 1 standard deviation HEC was 14.98 milligrams per cubic meter, with a total combined uncertainty factor of 30. The 2024 ATSDR stated that none of the models for these endpoints from the Zhang study provided adequate fit. Therefore, data were run using the Bayesian benchmark dose modeling online software. Similarly, just as in the draft 2022 ATSCR toxicological profile for 1,2-dichloroethane. In 2024, a chronic duration inhalation MRL was not derived. As a note, EPA has not evaluated the Zong et al. 2022 study since our systematic review does not cover the years between 2019 and 2022. Next slide, please. In summary, the suite of effects EPA identified included kidney toxicity, immunotoxicity, neurotoxicity, and male reproductive toxicity as the most sensitive, critical, non-cancer human health hazard outcomes associated with 1,2-dichloroethane. Inferences across evidence streams and the overall weight of evidence scientific judgment for these critical endpoints indicates that 1,2-dichloroethane is likely to cause these effects. I refer you to Appendix M.6 in the draft risk evaluation for additional information. Overall, 1,2-dichloroethane provides human health protective non-cancer points of departure for 1,1-dichloroethane. And with that, I thank you for your attention.
Thank you. And apologies for mispronouncing your last name. I took a guess and I 50-50 chance and I was wrong. I'll try to get it right next time.
You're just staying here and then they would make the game.
So let's see if we have questions. Yes, I see Dr. Landis has a question.
At least I'm consistent. So let me compliment your presentation and especially slide 85. That is an excellent example. That is a good example of the dose response curve. And I would present it differently. I also think the discussion here about why a NOAC to use that, it would be not a good case. So this is what I think of as a BMDL evaluation with a dose response curve. And I see that it was taken from the data in the paper, and you could see the experiment was designed for ANOVA. So that creates some limitations. So this is the kind of information I was looking at for the other studies. So I just wanted, I guess my curiosity was, or my question is this the standard way of looking at it now? Because it didn't, from what my reading of this document, that this was not the standard approach, perhaps, especially for the environmental toxicology data. And I don't see a very detailed evaluation of that data set because those are other kinds of uncertainties that are not addressed here. And my last question is, did you guys do a confidence interval for the regression and just didn't show it? Because that would also be very helpful. Thank you.
So
We seem to have lost our EPA folks.
That's okay. And I know EPA does this stuff all the time, so I was just looking for it to show up.
We're just conferring here.
We're just conferring. Yeah, so the BMD supplemental file that accompanies the draft RE has in any instances where the data were able to be modeled, these kinds of graphs are available for every single point of departure that was actually modeled. I don't know if that answered your entire question. I didn't catch it all. I'm sorry.
I guess I'm asking because when I read the risk assessment text for much of this document, it doesn't really, I guess I'm looking for the details so I can evaluate that assessment and the information used for that assessment. And to me, those are the kinds of things that are included in the uncertainty analyses. But what I see in the uncertainty analyses in this document, especially the environmental stuff that I really focus on, it doesn't include the details for the curve fitting. That would be a much better description than having 3 pluses or a minus, which is not quantitative at all. So I guess I'm asking, well, never mind. I guess I'm trying to get an understanding of why you're presenting it in this fact, where someone like me immediately wants to understand the intrinsic uncertainty of the regressions So when I look at pluses and minuses, I have some context that they're working in. So that's my clarification I'm trying to get at.
We can certainly provide more information, but the reason why that data were graphed for this presentation is because that is the point of departure that we use.
Right.
And again, if there are other points of departure that were able to be modeled, those graphs and the modeling for all those other points of departure are presented in the supplemental file.
Right.
And in terms of the environmental question that you had, I would defer to Jen on that one.
Yeah.
Hi, this is Jennifer Brennan, US EPA. I'm happy to answer Dr. Landis your question. So for several of our concentrations of concern or other environmental hazard thresholds, we generally don't model. We use the concentrations as reported by the authors. Now, where we did model was in our species sensitivity distribution, and those details are provided in the appendix for the species sensitivity distribution curve fitting.
Right, Dr. Brennan, I went through those in some detail already. And because, that helps me a lot, because I don't assume that information in the SSD, it's mostly modeled information. And I'm trying to get at if those response curves were used to generate that in the things you had data for, and because you don't show this except in the POD derivations, it's very difficult to me to evaluate the uncertainty and the quality of that information. So I think I understand the context better now. Thank you. I don't mean to sound negative, but I've just been a reviewer and stuff for maybe too long. And it's not negative. I'm just trying to get the information. This is an amazing piece of work. Yeah.
So this is George Cobb. Maybe to circle back to that topic just a little bit for Dr. Brennan, and not to continue to put you on the spot, but is it fair to say that in your species distribution analysis, you're using the LC or the EC50, whatever that EC may be, as a single point in the distribution and not using the entire distribution around each point?
Hi, Dr. Cobb. So if you look at the data points that are plotted within the SSD, these are LC50s, mainly where we make an exception. So for mortality, short-term mortality, and where we make an exception is for immobilization of our aquatic invertebrates. We substitute that in as sufficient. Confidence intervals are plotted around the SSD as when the curve is fitted. But yes, it's made up of the LC50 and EC50 points.
But individual points for each LC or EC50?
The only time we would have a distribution around the individual points is if that data point consisted of several LC50s for that species that were compiled in a geometric mean, and that is taken into account.
Excellent. Yeah, thank you very much for that. Okay, Dr. Rose is next.
Yep. So, strange that my camera is still not working. I had exited and re-entered the meeting, and it still is not working. So back to the inhalation assessment. So thank you very much for the presentation. I just had a very specific question that was on slide 80. Talking about the acute inhalation study and looking at the extrapolation of the dose to the human equivalent concentration. And I noted that there was an allometric body weight scaling that was applied there, but that the critical effect is a local effect to the respiratory tract. So I was curious about, is that a common way to adjust the dose when you have a local effect to the respiratory tract versus a systemic effect? And I will note that I didn't see that allometric body weight scaling in the document, in the risk evaluation document.
Yes, thank you for that question, Dr. Rose. So we consider this a neurological effect because of the tissue that it's impacting. And so that would be a standard adjustment that we would apply. And that should be described in the draft RE. I can't pinpoint an exact table for it now, but that would have been applied and described in the draft RE.
Okay. So I looked in the just for keyword search for allometric body weight scaling or dosimetric adjustment and couldn't find anything in the simulation.
Oh, excuse me. So in the point of departure tables that are in the body of the report for the 3 different durations, the body weight to the 3/4 adjustments was indicated in the footnotes to those tables.
Okay. Okay. I will definitely check that. Thank you.
All right. Thank you for that question and the answer, Dr. Anatole. Let's go to Dr. Fox.
Hi, yeah, so I have it's more of a general question. So we've seen now a couple of instances where the final ATSDR document is different from the draft. And you've mentioned that the systematic review that fed into the documents we're reviewing only went to 2019 or went to 2019, right? But my question is more general than that. So just sort of how does the program, take into account the final ATSDR document, or do you not take it into account?
We phone a friend.
Yes.
Hi, Dr. Fox, it's Anna Lowett, Senior Science Advisor at EPA. So.
Oh, we lost you.
Oh, we're having some muting issues on our little microphone over here. Sorry about that. I hear 2 parts to your question. One is how do we use ATSDR? And then one is how do we supplement our systematic review? Know that we're missing a few years. So I would take that in 2 parts. So you'll notice that a couple of our questions have subparts on how to incorporate or not the ATSDR assessment that our team has come to different conclusions on some key studies that you've heard from both Ollie and Kathy over the course of the day. And we're looking for your feedback on that. But with respect to filling in years, we recognize that between now and final, we're going to have to do a supplemental search. Like, for example, you heard in Kathy's presentation, there's a Zhang study from 2022 that's brand new that might be quite useful, that is not part of our assessment. So we will have to do that supplemental search, and the extent to which that will or won't affect what we're doing is yet to be seen, I think. But to the extent that either the public commenters or members of this panel know other studies on either the 1.1 or the 1.2 that we're missing, we'd love to hear about those.
Okay, thank you.
Right. Are there other questions from the committee? So this is George Cobb, and I have a quick question. It's more perhaps just a clarification. On slide 95, I think there may be a unit mismatch, and this is not a gotcha. This is just make sure everything's correct for the record. It looks like that 0.04 milligrams per kilogram per day that's bolded. Is that supposed to be milligrams per kilogram per day? Or is that supposed to be milligrams per cubic meter? I see the same different units on the same looking text in that slide.
Correct. That is a typo on the slide. That should be milligrams per meter cubed. Thank you.
And Dr. Anatole, that's what you said. I just happened to notice it because it was bold, and just I don't know if there's a need to correct that for the record, but in this context of your excellent presentation, that's a minor thing, just for clarification.
Great, thank you, Dr. Cobb.
All right, and so thanks for that excellent presentation and dialogue about that particular question. We are now at or near a break time. We're about 10 minutes ahead of schedule, but I think it's probably time to go ahead and take that break now. And it's scheduled for 15 minutes. And let's go ahead and take the entire 15 minutes and come back. And then we'll start talking about the in vitro studies, dermal absorption and in vitro studies.
Happy did something.
Welcome back from our break at the Science Advisory Committee for Chemicals. We're dealing with the 1,1-dichloroethane topic today. And I'd like to first ask our DFO, Ali Munir, if there's anything that we need to be paying attention to or anything that we need to address from her perspective. Seems like Ali's not there, so we can proceed on. Oh, there. Well, do we have Ali? It seems like you're on mute, Ali. Not on Zoom, maybe your computer. Looks like you're still on mute. I think it must be your computer or your microphone on your headset, but that's okay. We'll just proceed and come back. If you have anything for us, just let us know. Okay. I think before we go on any further, just quickly, are there any questions from the committee about anything that we've talked about so far today? Okay, if not now, let's move on to the presentation about the dermal absorption aspects, and that will be Dr. Irwin.
Doing the cancer assessment.
Oh, wait, you know what? I'm very sorry. That's right. This cancer assessment was the second half of
Exactly.
what you did. So it's Dr. Anatole, and it is the cancer assessment, which was slated just before the break. And so we'll do that now, and then we will move to Dr. Irwin after we take questions for the cancer from. So please, Dr. Anatole.
Thank you. Could I have slide 99, please? Okay, so moving into the cancer assessment for 1,1-dichloroethane, there was a single NTP study conducted in 1978 in rats and mice by the oral route. The rat portion of the study rated uninformative in our systematic review based on a number of factors that included a high incidence of pneumonia and decreased survival rates. As a result, the data in rats were not usable for risk assessment. The mouse portion of the study, however, rated high in our systematic review, but there was no evidence of cancer observed in mice, only evidence of precancer endometrial polyps reported. And however, this endpoint cannot be used for cancer slope factor calculations. And there were no cancer studies via the inhalation or dermal exposure routes available for 1,1-dichloroethane. Next slide, please. So in order to calculate a cancer slope factor for 1,1-dichloroethane, EPA used a read-across approach and evaluated the available cancer data for 1,2-dichloroethane. That database consisted of a single carcinogenicity study in rats and mice by NTP. And as with the rat portion of the 1,1-dichloroethane study, the rat portion in this study rated uninformative in our systematic review based on high incidences of pneumonia and decreased survival rates. The mouse portion of this study, however, rated high in our systematic review. Female mice also exhibited endometrial polyps, as with 1,1-dichloroethane. But in this study, there was evidence of cancer that included statistically significant increases in a variety of tumors, such as squamous cell carcinomas of the forestomach, circulatory system hemangiosarcomas, mammary gland adenocarcinomas, and lung and liver tumors. As a result, EPA used the hepatocellular carcinomas in male mice from this oral study in 1,2-dichloroethane as a basis for calculating a cancer slope factor for 1,1-dichloroethane. And I should also note that IRIS utilized the same study to calculate a cancer slope factor. Next slide, please. And as you can see in the graphic on this slide, the data for hepatocellular carcinomas in mice show a very good dose response. Next slide, please. As previously mentioned, there are no cancer data by the inhalation route for 1,1-dichloroethane, so the read-across approach utilizing available cancer data by the inhalation route for 1,2-dichloroethane was used. For 1,2-dichloroethane, there is a single cancer study by the inhalation route. This study rated high in our systematic review. A variety of tumors were observed, and EPA used a combination of these tumors to calculate the inhalation unit risk for 1,1-dichloroethane. Next slide, please. So this slide is a summary of what was just discussed that EPA used for the cancer slope factor and inhalation unit risk for 1,1-dichloroethane based on read across from cancer data for 1,2-dichloroethane. The cancer slope factor and inhalation unit risk are derived based on continuous exposure scenarios. Due to the exposure averaging time adjustments incorporated into lifetime exposure estimates, separate cancer hazard values for occupational scenarios are not required. The oral cancer slope factor for mice is based on read across using cancer points of departure from the 1,2-dichloroethane based on hepatocellular carcinomas in male mice from the NTP 1978 study. Due to scarcity of data, route-to-route extrapolation from the oral slope factor is used for the dermal route. Read across using cancer inhalation points of departure from 1,2-dichloroethane are based on combined mammary gland adenomas, fibroadenomas, and adenocarcinomas and subcutaneous fibromas in female mice from Nagano et al. In 2006. The oral cancer slope factor for 1,2-dichloroethane was used to calculate a drinking water unit risk of 1.8 e to the -6 per microgram per liter, using a drinking water intake of 2 liters per day and a body weight of 70 kilograms. Next slide, please. EPA consulted with an internal EPA ad hoc committee comprised of technical experts from EPA's Office of Pesticide Programs, Health Effects Division, and the Office of Research and Development to evaluate the individual study quality and use of the available carcinogenicity studies for 1,1 and 1,2-dichloroethane. OPPT identified 3 primary studies for their consideration. The available studies listed included an oral bioassay in rats and mice for 1,1 and 1,2-dichloroethane and an inhalation bioassay in rats and mice for 1,2-dichloroethane. A memorandum that summarizes the internal EPA ad hoc committee comments and the OPPT responses are part of the supplemental file that accompanies the draft risk evaluation. Next slide, please. So starting with the first study, the 1978 NTP oral bioassay of 1,1-dichloroethane in rats and mice, the ad hoc committee concluded that the data from the oral study in rats for 1,1-dichloroethane are not appropriate for use in quantitative risk assessment based on the high incidences of pneumonia and decreased survival observed in all dose groups, including control. The ad hoc committee also concluded that the data from the oral study in mice for 1,1-dichloroethane were not appropriate for use in quantitative risk assessments since there was no conclusive evidence of carcinogenicity. And in addition, the ad hoc committee concluded the qualitative use of the data is not appropriate. And again, there is a supplemental file with additional details that are accompanies the draft risk evaluation. Next slide. Now moving on to the second study, the NTP 1978 oral bioassay of 1,2-dichloroethane in rats and mice. The ad hoc committee concluded that the data from the oral study in rats for 1,2-dichloroethane were not appropriate for use in quantitative risk assessment based on the high incidences for pneumonia and decreased survival observed in all dose groups, including control. The ad hoc committee also concluded that the data from the oral study in mice for 1,2-dichloroethane were not appropriate for use in quantitative risk assessment based on several guideline and methodological reasons. Next slide, please. And finally, the third study, the ad hoc committee was asked to evaluate the 2-year inhalation carcinogenicity study in 2006 by Nagano et al. The ad hoc committee concluded that the data in the inhalation study in rats and mice were appropriate for use for quantitative risk assessment. Next slide, please. So just to recap, the ad hoc committee concluded that oral studies in rats for both 1,1 and 1,2 dichloroethane were not appropriate for use for quantitative cancer risk estimate. And the oral study in mice for 1,1 dichloroethane is not appropriate for use for quantitative risk assessment to derive an oral cancer slope factor. However, EPA is proposing to use the study in mice for 1,1 dichloroethane qualitatively, since this study rated high in our systematic review. The ad hoc committee also concluded that the oral study in mice for 1,2 dichloroethane is not appropriate for use for quantitative or qualitative cancer risk assessment. However, EPA's systematic review rated the mouse study in 1,2 dichloroethane as high. I should note that IRIS concluded that 1,2 dichloroethane is a probable carcinogen in 1987, and that the NTP 1978 1,2 dichloroethane oral study in mice was the basis for the IRIS oral slope factor. EPA is proposing to use this same study for this draft risk evaluation. And finally, the ad hoc committee concluded that the inhalation study in rats and mice for 1,2 dichloroethane is appropriate for use to derive an inhalation unit risk. So let me direct you to charge questions 9A through 9G, where EPA is soliciting comments from the SACC on the evaluation of the individual study quality and use of the available carcinogenicity studies for 1,1 dichloroethane and 1,2 dichloroethane that were just briefly summarized here. And again, additional details regarding the evaluation of these studies are outlined in the EPA peer review of carcinogenicity studies supplemental file that accompanies the 1,1 dichloroethane draft risk evaluation. Next slide, please. So just to recap what Dr. Irwin discussed earlier in the presentation, this slide summarizes the common cancer endpoints between 1,1 dichloroethane and 1,2 dichloroethane, supporting the use of 1,2 dichloroethane carcinogenicity data as read across for 1,1 dichloroethane. As a result, from among many other lines of evidence, EPA has high confidence that the 1,2 dichloroethane data will be human health protective for 1,1 dichloroethane exposures. Next slide, please. So just to summarize overall non-cancer and cancer human health hazard key points and conclusions. Acceptable human health hazard data were not available to assess non-cancer or cancer risks for 1,1 dichloroethane. Therefore, a read-across approach where data available for a closely related chemical or analog, 1,2 dichloroethane, was used to evaluate the human health hazard of 1,1 dichloroethane. The analysis of other chlorinated solvents as potential analogs for read-across followed the general principles for read-across that took into consideration structural similarities, physical chemical properties, metabolism, and toxicological similarities and adequate data availability. The analysis resulted in the identification of 1,2 dichloroethane as the most appropriate analog to fill the identified data gaps for 1,1 dichloroethane. EPA has high confidence that the 1,2 dichloroethane data will accurately reflect both the non-cancer and cancer hazards of 1,2 dichloroethane and will be human health protective for 1,1 dichloroethane exposures. And with that, I thank you.
All right. Thank you for that presentation. And now we'll turn to the committee to see if there are any questions related to this presentation. So this is George Cobb again. I would ask on slide 108, am I reading that correctly? That, and this is not a part of the document that I had a chance to read, that the assessment was that the NTP study for mice, that third bullet, is not appropriate for use, but then you did actually use that one for the risk evaluation? Am I misreading that?
Yes, that's correct. The oral mouse study for 1,2 was deemed not appropriate, but by the EPA internal ad hoc committee.
Right,
and it did rate high in our systematic review. And the discussion of their concerns, their methodological concerns, and our response to that are found in the supplemental file, the memorandum
Excellent. Thank you. Can you just very briefly relay what those methodological or guideline reasons were, if you have those in memory?
I do. I think the concern was that a lot of the methodological concerns that they had were actually conflated with the data for 1-1. And so we went through very distinct, comment and response within that memo. So it's outlined very clearly for you. There's several of them.
Okay, thank you. But part of the reason I asked that is on the last meeting, we were asked whether mouse data or other kind of data that might not be as good as rat data would be appropriate for use this way. So I'll certainly look at that. I see Dr. Apte has his hand up.
Yeah, there is a separate document that's that's referred to here, where they discuss all of this, where what was the charge for the ECRAD and what the committee did and etc. And I can send it to you, which has the table where there is specific things that they have.
Dr. Apte, I can find that. I just was curious for this discussion here.
Oh, okay.
But I can
have it right in front of me if you want me to go in.
Okay, thank you. Okay, are there other questions? If not, I'd like to thank you, Dr. Anatole, and then we'll move to now we'll move to Dr. Irwin.
Okay, I'm back. Thank you. I'm William Irwin, toxicologist from EPA and ECRAD. I'll be presenting the EPA interpretation of the in vitro dermal absorption test order data for 1,1 dichloroethane. This is data on the risk evaluation chemical itself. Next slide. So this slide presents a summary of the dermal absorption study results. The testing followed OECD 428, which specifically states the testing should be that to which humans or potential target species may be exposed. So the 1,1 dichloroethane conditions of use, or COU, is to the neat or the pure 1,1 dichloroethane. The neat or pure 1,1 dichloroethane raw mean dermal absorption was 0.13% at a mass recovery of 58.4% on average across the replicates. The neat 1,1 dichloroethane raw dermal absorption replicate range was 0.08% to 0.21%. So EPA corrected the absorption so that only a portion of the missing mass is considered absorbed. The mean corrected absorption is 0.22%, with the corrected absorption range of 0.14% to 0.63%. And this variability perhaps could be due to susceptible subpopulations. The dermal absorption of the analog 1,2 dichloroethane is very similar at 0.21%. And this is documented in the ATSDR reports, which we did consult frequently. So OECD guidance document 156 comments on data variability. The use of the upper confidence limit, 95% confidence interval, addresses uncertainty about the mean absorption due to sampling variability. This approach is reasonably conservative and could reduce the need to repeat studies. So that's a quote from the OECD guidance. So the OECD, or the 1,1 dichloroethane coefficient of variation in the cohorts all exceeded the OECD limit of 25% coefficient of variation. For neat 1,1 dichloroethane, the 95% upper confidence level is calculated to be 0.13% dermal absorption. And if you look at the document 32 posted in the document, there's a lot of details on how these calculations were done. Next slide, please. So there's different approaches where you can analyze the absorption data when there's missing mass. So one route is to assume the missing mass is not absorbed, and citing some of the guidance documents, OECD 156. If recovery is less than 95%, but a robust explanation demonstrating the missing material will not have been or very unlikely to have been absorbed, an inclusion of the missing material might not be required. Also, there's a quote from EFSA guidance on dermal absorption. Losses that are considered to be from non-absorbed material will have no impact on the results. However, the 1,1-dichloroethane testing did quantify the non-absorbed material in the vapor trap, the donor chamber washings, and the skin washings. And that did quantify the non-absorbed material. So the second approach is to assume only a portion of the missing material is absorbed. And citing OECD guidance document 156, the quote is, one approach would be to normalize the measured dermal absorption value for losses. This approach assumes that losses occurred in all matrices equally, which means the various compartments. So for neat 1,1-dichloroethane results, all replicates had less than 80% recovery. So there was some comment in the guidance that you could perhaps exclude statistically replicates that had less than 80% recovery, but in this case, all of them were less than 80% recovery. So anyway, approach 2, EPA chose this approach as appropriate and reasonable. And then on the other end of the spectrum is assume all of the missing mass is absorbed. And OECD guidance document 156 states, as a second approach would be to include all unrecovered material in the amount that is potentially absorbed. And then EFSA guidance, there's a quote, adding the missing material should certainly apply when the calculated dermal absorption value is less than 5% and recovery is less than 95%. However, this approach is very conservative, assuming all the missing mass is absorbed. So, and again, there's no high recovery data over 80% for the neat 1,1-dichloroethane condition of use to base the calculations. So recovery data replicates could not be excluded. So next slide, please. So this slide lists the raw data results from the OECD 428 testing for 1,1-dichloroethane. For the condition of use, neat or pure 1-dichloroethane, the mean raw absorption is 0.13% at the mass balance of 58.42% recovery. The neat replicant range was 0.08% to 0.21% absorption. The absorption for non-COU samples at lower values of 0.01% to 0.12%. Percent coefficient of variation across all replicates and testing ranged from 38% to a very high value of 200%. The lowest coefficient of variation was actually for the neat 1,1-dichloroethane testing, which is the condition of use in the risk evaluation. OECD guidance document 156 cited in the test order was followed for the data calculations. So overall, an intermediate dermal absorption value of 0.3% was utilized for the risk calculations. The data in the IPM vehicle and at concentrations of 1% or 10% are not conditions of use. And on top of that, they also tend to have high coefficient of variation results. So, and obviously the guidance in the European Union, TSCA is not required to follow them. So next slide, please. So this slide shows mass balance results and variability across replicate testing for NEAT and 50% 1,1-dichloroethane cohort samples for the in vitro dermal absorption. So the green bars are the raw data results, and the black bars are the paired data corrected for missing mass for each replicate. And there's 6 replicates for each of these 2 cohorts. So for the mass balance corrected data for NEAT 1,1-dichloroethane, the replicate results were 0.14% to 0.36% absorption, as shown in the graph. So importantly, the testing had a much lower and sensitive limit of detection, or LOD, at 0.008%. So in some of the guidance documents, it comments on correcting the data rather than rejecting the study entirely and repeating it. So in context, some of the an exposure model predicted a dermal absorption of 0.6%. So, and thank you for your consideration.
Right. Thank you for that presentation about the dermal absorption. Are there questions from the committee about this information? I see Dr. Lee. I think you're still on mute, Dr. Lee.
Yeah, so this is Lee, a member from SACC. So I do have 2 questions regarding the presentation. So first, thank you so much for the presentation. So can you go back to page 114 at the slide? Yeah. Yeah, so you mentioned that the third approach was not used because it's very conservative, as shown on the screen. So I seeking explanation or justification for not using this approach. Because if you go back to OECD recommendation, they recommend excluding this method only if, quote, a robust explanation demonstrate that the missing material would not have been or is very unlikely to have been absorbed, quote ends. So that's why I was wondering whether you have a robust explanation for this. Or do you want me to finish my second question, or do you want to answer the first question first?
Let's take them one at a time. Sure. So the as explained in the slide, the non-absorbed material was quantified in the various compartments of the testing apparatus. So the vapor trap, the donor chamber, and the skin. So the non-absorbed material was specifically quantified. So we concluded that option number 1 seemingly was not appropriate. Conversely, option number 3 is extremely conservative. If you assumed all the missing mass was actually absorbed, it would be about 42% dermal absorption. And comparing it to some of the other chemicals, like the analog chemical 1,2-DCA, it had 0.21% dermal absorption. So if we read across from the 1-2 DCA data study, that doesn't seem to be an accurate or appropriate result. So.
Okay, thanks so much for the information. So you mean that if you read across from another chemical or you compare this number with other chemical, and you will find approach 3 would give a very, very high estimate, which is 42%, which is much, much higher than the numbers for other chemicals, right?
Yes, right. So if you look at some of the dermal models, they're based on the inputs of molecular weight and log KOW information. So 1-2 DCA obviously has an identical molecular weight and has a very similar log KOW value. So we expect that the dermal absorption of 1-1 DCA should be very close to that of 1-2 DCA. So.
Okay, yeah. So I had this question because I think this explanation or justification was missing from the report, the written report, or from the slides. Yeah. And my second question.
So we're gonna talk about this more when we get to the charge questions, but go ahead. Sorry.
Yeah, my second question is regarding page 116. So on that slides, page 116, so on that slides, a very high number that is correct. So the number after correction for the recovery, a very high number of almost 0.6%, which is 0.59 or something percent, is excluded, probably because the COU is not relevant for the exposure, because it's not a neat chemical. It's 50% in 1,2 DCA.
Right. So
is that the reason this data point was excluded from the final estimate?
Yes. So the point of this figure was just to show the variability in the data. We added the other cohort at 50% concentration just to show those results, to demonstrate that. But the condition of use is to the neat or the pure 1,1 DCA. So.
Okay, thanks for the clarification.
So thank you. And I've got some questions to come back to, but I want to let Dr. Kalushny ask her question.
Yes, Yulia Kalushny, thank you for presentation. That is very difficult topic because I think from the beginning we started with in vitro study, which is far from being ideal. So I have like a couple questions, actually maybe more than 2, but they're small and they kind of relate to each other. So the first one would be I don't understand maybe why exactly the interest only in neat material. As I understand, exposure to different concentrations and dilutions are very possible. At the same time, this LabCorp study is using multiple concentrations, and I thought it's important the neat material is actually can easily be diluted in own sweat. That's already dilution. Plus, as actually can be seen on page 116, that some dilutions actually have high absorptions, and it's pretty common, and that presenting higher human risk. So that's basically I guess that's like one complex question. Why only neat? Why to test so many different concentrations and solvents, spent so much time. The study lasted a year, but the need condition was limited, and data and testing would not spend time on that, because it is hard to believe that in this day and age, with all equipment and pipetting techniques, it should not be impossible to get mass recovery at least close to desired value, and to have more reproducible data, just by playing with exposure volumes and everything else, which we're not going to discuss now. Thank you.
Yes, thank you. We were confirmed. So the NEAT 101 DCA is the condition of use and the risk evaluation. So that's why we tested NEAT. We also tested other concentrations as well.
So this is George Cobb. I think the question is, why exclude the diluted versions? Because that is possible with, for instance, sweat or other scenarios. So that, I think that was the question.
So our exposure people and engineers, they'll answer some of these questions of the conditions of use later on.
So will that be when the charge question is asked then?
Presentation.
Say it again. One more time.
And then we will.
Yeah, it'll be the next presentation.
It's the next.
Oh, the next presentation.
Yeah.
Yes, today.
Oh, okay. I'm sorry. I missed that was going to be part of it. Okay. Well, if that's okay, Dr. Kaluzny, we'll go to wait for that presentation to get to that particular answer.
Yes, thank you. I just wanted to, maybe there is more explanation need to be made,
Sure.
because on the study, NEAT is actually looks like afterthought.
So I had similar questions, so it will be good to hear what the next presentation had.
Definitely. Thank you.
Thank you. And then Dr. Semmel?
Yes, thank you very much. And thank you for the presentation. It was helpful and did provide some good clarifications. A couple of my questions were closely related to what Dr. Kaluzny was just asking. So I look forward to the next presentation as well. But the final question I had that I don't think is related to what she was asking is, how did the agency take into account the loading of the skin that was, or the in vitro cell that was performed in the in vitro study compared to the loading in the condition of use or in the occupational exposure scenario, the OES, that was ultimately considered for the purposes of exposure.
Yes, that'll be covered in the next presentation. So the engineers and exposure people cover that part of the testing recommendations.
Okay, thank you very much.
All right, so so this is George Cobb again. We'll circle back to those two questions when and hope that they are answered in the next presentation. If not, we can have a little more discussion. So Dr. Irwin, thank you for that presentation. And I guess now we can move into the final presentation about occupational exposure. And that will be by Greg Masick. Do we have a presenter?
Yes, I'm here.
Yes. Welcome.
Thank you. Hello, my name is Greg Masick. I am a chemical engineer assessor within EPA's Office of Pollution Prevention and Toxics, and specifically in the existing chemicals risk assessment division. I will be presenting the slides on the occupational exposure assessment that we've done for 1,1-dichloroethane. And these slides pertain to the occupational exposure charge questions, which are questions 10A, 10B, and 10C. Next slide. In this slide, I identify four main objectives for the occupational exposure assessment. The first objective was to identify the occupational exposure scenarios that we would assess for 1,1-dichloroethane. Second objective was to identify similar exposure groups, SEGs, for each OES, occupational exposure scenario. Our ability to identify SEGs was dependent on whether the source of data had sufficient detail. If not, our default, as has been our practice in EPA risk evaluations, was to assess exposures for the generic SEGs of what we call the workers, which are individuals who are directly involved, as we define it, in manufacturing the chemical or potentially exposed during downstream industrial uses, or occupational non-users. And these are individuals who do not directly handle a chemical, but who perform work in an area where the chemical is present. The third objective then was to estimate the levels of inhalation exposure and dermal exposure for the similar exposure groups within the OESs. And our standard practice to estimate both a high end and a central tendency exposure estimate. And then the fourth objective was to then evaluate the weight of scientific evidence for the assessment for each OES. Next slide. So our task is to assess the conditions of use for the chemical. EPA determines the occupational exposure scenarios to assess that are associated with the conditions of use. The OES determinations are largely driven by similarities and differences in release and exposure potential between conditions of use, and the availability of data and modeling approaches to assess releases and exposures. Generally, we follow three approaches. We may designate the condition of use as an OES to assess. For example, the condition of use of manufacture that results in the OES of manufacture. We also may group multiple conditions of use into one OES. An example of this is where we group multiple conditions of use associated with processing as a reactive intermediate into one OES. And then we also may take one COU and break it down into multiple OESs. One example of this has been the COU of degreasing solvent. Doesn't directly apply in 1,1-DCA, but it's an example where we break down this condition of use into multiple OESs, such as open top, vapor degreaser, closed system, cold cleaning, aerosol degreasing. Next slide. So this slide has the results of our identification of OESs. The 1,1-DCA life cycle can be characterized as follows. There's manufacturing. It's primarily used as a reactive intermediate. There's commercial use as a laboratory chemical, which would involve a repackaging step. There's distribution and commerce, and then waste disposal, where we identified several different OESs under that main OES. So we had a total of 8 OESs that we assessed for 1,1-DCA. Next slide. So this slide provides information on the general approach that we follow to assess inhalation exposure. Our first step is to identify inhalation monitoring data that can be used for the assessment. And our preference is to use full shift personal breathing zone monitoring data. Our hierarchy consists of data on the chemical of interest for the OES being assessed. For example, 1,1-DCA data from manufacturer to assess the OES of manufacturer. Underneath that is where we have data on the chemical of interest, but we apply it to a similar OES as analogous data. An example of that is where we may use manufacturer data for 1,1-DCA, apply it to processing as a reactive intermediate. When data on the chemical of interest is lacking, we fill data gaps with surrogate monitoring data. This is data for a similar chemical to the chemical of interest for the same OES. We also may use area monitoring data in an assessment, but there's more uncertainty as it monitors a location rather than a person. And then we may use modeling approaches. These may be deterministic modeling approaches or probabilistic modeling approaches. And another option that we may use in some cases is the use of occupational exposure limits. These could be company-specific for site-specific assessments, OSHA PELs, voluntary limits. Next slide. So now I'll go more into specifics of how we applied the general approach for assessing inhalation exposure to 1,1-DCA. And the next several slides will describe how we did this. In this slide covers that we had data on inhalation exposure to 1,1-dichloroethane during manufacture that was provided to EPA from the Vinyl Institute through a test order. So this was data on manufacture. We used it to assess the OES of manufacture. This data is considered primary data, meaning that it was collected for the purpose of risk evaluation. EPA reviewed and approved the sampling protocol. EPA has received and reviewed the summary report. And it includes all the key metadata that we need in our occupational exposure assessments. The test order monitoring study monitored 4 different similar exposure groups at the facility. This included operators and process technicians, maintenance technicians, laboratory technicians, ONUs, A total of 62 full shift personal breathing zone samples were collected, and the data was rated as high quality per our EPA data quality ratings for occupational exposure data. Next slide. I want to note that we did receive additional 1,1-dichloroethane monitoring data from the test orders. And this was data on 1,1-dichloroethane inhalation exposure during production of 1,1-DCA as a byproduct from manufacture of 1,2-dichloroethane. And this data will be included in the 1,2-dichloroethane risk evaluation. And that relates back to a decision that was made during the scoping for 1,2-dichloroethane that the byproducts of 1,2-dichloroethane manufacturing would be assessed in the 1,2-dichloroethane risk evaluation. Next slide. So the previous slides described the monitoring data that we had for 1,1-dichloroethane. The next step in our assessment approach, the previous slides mentioned the 1,1-DCA data we got from the test orders. Now, the next step in our assessment approach was to include 1,1-dichloroethane monitoring data from secondary data sources. So secondary data is monitoring data that has been previously collected. The data was not necessarily collected specifically for use in an EPA risk evaluation. And it's available to us to EPA through public databases such as the OSHA CEHD data, chemical exposure health data, NIOSH publications, scientific literature. We've also received data through comments on risk evaluation documents. So this data can still be rated as high quality, but often lacks key metadata, resulting in lower data quality ratings. The results of our efforts to identify additional 1,1-dichloroethane monitoring data from secondary data sources, it resulted we weren't able to identify any additional data. So overall, the only 1,1-DCA inhalation monitoring data that we had was from the test order. Next slide. This slide covers how we applied the test order data to the OESs. So the test order gave us data, it was from manufacturer, and so it gave us data that we could use to assess the 1,1-DCA inhalation exposure for the OES of manufacturer. We then considered whether we could use that data to assess exposure for other OESs. And so we applied it, as I previously mentioned, to the OES of reactive processing as a reactive intermediate. This was considered to be analogous to the manufacturer OES. And this is consistent with approaches we've taken in previous risk evaluations. For example, in the perchloroethylene risk evaluation, we actually had data on exposure to PCE from processing as reactive intermediate, and we applied it to manufacture as well. And then one of the SEGs for the test order data was laboratory technicians. So we applied this data to assess 1,1-DCA inhalation exposure for the OES of laboratory chemical use. Next slide. So for the remaining OESs where we did not have 1,1-DCA inhalation monitoring data to apply, we sought to do the assessment, filling data gaps with other approaches. One of the approaches we look to in filling data gaps is the use of surrogate monitoring data. This approach involves using inhalation monitoring data for a similar chemical, but collected for the same OES. And when we search for surrogate data, we're focusing on EPA published risk evaluations, which may be either draft or final. And so as we've gained experience with risk evaluations, we're completing more and more and have more and more surrogate data available if we don't have data for the chemical of interest. And that's related to one of the charge questions, which covers use of surrogate data. And we can also consider, we also will look to results from systematic review for chemicals that we're currently working on, or we may not have yet published. So that would include other chlorinated solvents like 1,2-DCA that we're working on. We do have a method for applying surrogate data to the chemical being assessed. It does account for vapor pressure differences. Our method does not include combining chemical-specific data with surrogate data to estimate exposures for an OES. So if we have chemical-specific data, like 1,1-DCA, we just use that, even though we may have also had surrogate data from past risk evaluations that assessed, say, the manufacturer OES. So in 1,1-DCA, we use surrogate data approach for 2 of the waste disposal OESs. We had data on methylene chloride and 1,2-dichloroethane, and they were used to assess the OESs under waste handling, treatment, and disposal. Next slide. Another method that we use to fill data gaps is the use of modeling. We use the probabilistic modeling approach to assess 1,1-DCA inhalation exposure for the OES of repackaging. EPA has a generic scenario for repackaging, and this aids in model setup and execution. A generic scenario models inhalation exposure in the repackaging for worker activities of unloading, container cleaning, and loading. In this type of modeling approach, models for each individual worker activity were executed in a probabilistic mode with Monte Carlo technique using 100,000 iterations. That's our standard, with each iteration representing a different combination of parameter values. The model estimates exposures and durations for each of the individual worker activities. Assumption that we make is that a worker can perform each of the activities, so the exposures for individual activities are added together and averaged over 8 hours to estimate the full shift 8-hour time-weighted average exposure. Next slide. Now I will go into the assessment of dermal exposure for 1,1-DCA. 1,1-DCA is a highly volatile liquid. There was no dermal monitoring data relative to the occupational dermal exposure assessment that we're able to identify from review of the scientific literature. For highly volatile liquids, EPA uses the dermal exposure to volatile liquids model to estimate dermal exposure, and this model was applied for all OESs. As William covered in the previous presentation, we did receive data on fractional absorption for 1,1-dichloroethane from a test order, and the proposed dermal fraction absorption value of 0.3% was derived from the test order study data. And this is one of the parameters in the model. Next slide. So this is the dermal exposure to volatile liquids model. And I'll cover in the next slides each of the parameters in more detail. Next slide. This model, we executed in a deterministic mode. We used high-end skin surface areas and dermal loading values for the high-end dermal exposure estimate, and then we used the mid-range skin surface areas and dermal loading values for the central tendency dermal exposure estimate. The model estimates exposure to the hands and does not account for dermal exposure to other parts of the body. Next slide. So one of the parameters is the skin surface area, and this is a model default parameter. We use values from Chapter 7 of the Exposure Factors Handbook. A high-end value of 1,070 square centimeters. It's based on the mean two-hand surface area for adult males, ages 21 or older. For central tendency, EPA assumes the surface area equal to half of the high-end estimate. Next slide. This is the parameter of dermal loading onto the skin. This is also a model default value, and the values are based on experimental studies that are documented in a US EPA reference from '92. The experimental studies were done on a set of 3 non-aqueous liquids. The objective was to measure the quantity of chemical transferred to the skin. Initial wipe test was performed with subjects wiping their hands with a cloth saturated in the liquid. The amount of liquid retained on the hands was measured immediately after application, and the high-end values that we used in our model, 2.1 milligram per centimeter squared and the 1.4 milligrams per centimeter squared for central tendency, are based on the results of those experimental studies. Next slide. Next slide is, again, the fraction absorbed value, which came from the test order data. And this parameter is both a chemical specific and OES specific. So we're looking to use a fraction absorbed value that's specific for 1,1-DCA. And then and this relates to some discussion at the last presentation. We're also using a value that corresponds to the concentrations that we anticipate that the workers will be exposed to in handling, working with 1,1-DCA for a particular OES. And so for this particular assessment, we expected 1,1-DCA to be handled in neat 100% form for all OESs. And so we used the fraction absorbed value for the neat form of 1,1-DCA. Next slide. Another model parameter is the weight fraction. This is also an OES specific parameter, as I mentioned. And so our approach is to use the highest concentration for each OES. If 1,1-DCA went through formulation steps where it was formulated into a more dilute form, and then there were subsequent uses of dilute form of 1,1-DCA, then we would have modified the weight fraction accordingly. But for this particular assessment for 1,1-DCA, we assumed up to 100% for each OES. Next slide. So this slide provides a comparison of results obtained from using the model. For 1,1-dichloroethane, resulted in a high-end estimate of 6.7 milligrams per day for all OESs in a central tendency, 2.3 milligrams per day for all OESs. For comparison, if we had applied this model for a non-volatile liquid, where the fraction absorbed value would be 1, this would result in dermal exposure estimates of high-end 2247 milligrams per day, central tendency 749 milligrams per day. So you can get a sense of the comparison there. Okay, next slide. These are additional components of the occupational exposure assessment. One of which was estimating number of workers and ONUs. Chemical specific data on workers numbers can be available from data from the chemical data reporting rule. Data on the number of workers at the NAICS code or SACC code level for a given OES can be found in data from Bureau of Labor Statistics, US Census data. So we'll identify the NAICS code or SACC code that corresponds to the OES, and then we can look up data from these sources to get data on workers numbers for that OES. Another component is estimating the number of days per year of worker exposure. In general, the exposure frequency is the same as the number of operating days per year for a given OES. And we generally will put a cap at 250. We won't assume that a single worker would work more than 250 days per year. Next slide. So this slide has a lot of summary information on the occupational exposure assessment. It's organized by OES. So if you go down the first column on the left-hand side, you'll see each of the OESs that we assess quantitatively listed, and then going across the first section applies to the inhalation exposure assessment. And the first part of that is summarized monitoring data we had available for the actual chemical. The next section describes surrogate monitoring data that we had available. And then the third section under inhalation is where we use modeling. And then the final section there under dermal exposure reflects that we did modeling for all scenarios. Next slide. After we've concluded our assessment work, a key next step is then assessing the weight of scientific evidence. So we evaluate these, we determine a rating which are based on strengths, limitations, and uncertainties associated with the occupational exposure data. For example, a strength in this case was having primary chemical specific data for inhalation monitoring for manufacture from the test order. An uncertainty is applying exposure data on the lab workers from the test order at the manufacturing facility to assessing the OES of commercial laboratories. Strength can be using Monte Carlo modeling approach in capturing a range of parameter input values. So this table in this slide summarizes for inhalation exposure the weight of scientific evidence ratings. And that concludes the presentation of the slides that summarize the occupational exposure assessment for 1,1-dichloroethane. Thank you for your attention.
Thank you. Thank you for that presentation. We'll turn it over to the committee to see if there are questions. I know we had some that were deferred to this point, and let's make sure we've gotten those answered. And do we have questions from the committee? I see Mike Wright. Mike, are you there?
Yeah, I'm trying to enable my audio and video. The audio seems to be enabled, but the video does not. There we go.
There you go. You're on now.
Okay, first, let me congratulate you for a excuse me, for a very clear oral presentation and for a very clear written presentation in Chapter 5 of the draft RE. And I'm embarrassed to ask this question because it's pretty basic, but I'm not sure I've seen a description of this anywhere. How did EPA actually determine what was an OES or a COU or an SEG? A related one, how did EPA determine I'll call them all workers, but what workers fell into your worker category, and what workers fell into your occupational non-user category? Was that done by EPA itself? Was it done by the Vinyl Institute as part of the test order? Was it done by, for example, interviewing managers and experts from the different enterprises? What was the process for doing that? It may seem that that some of those things are pretty obvious, but to give one example, you've got a workplace that manufactures one of these chemicals. It produces waste as well. The waste is taken off in a truck. No, let me change that. That produces one of these chemicals. The chemical is loaded into a tanker truck. Somebody probably from the maintenance staff goes out, and he or she is the person who actually performs that operation. And then it goes to a facility that uses it as a chemical intermediate, and somebody else comes out and does that operation of essentially offloading it. Are those people engaged in manufacturing or use or in distribution and commerce? I mean, that's
Sure.
kind of questions about who goes where.
Yeah.
And, how do you determine that?
Yeah, great question. And I think that is one of our challenges to continue to work on communicating these points as clear as possible. So in this case, and that's why I wanted to emphasize the primary exposure data that we had available, and that was through the test order. So the test order process involved first, sending out the order that there would be requirements of inhalation monitoring data. But a key part of the test order process was then to develop the sampling protocol. And so through that process, there was correspondence back with the industry group, in this case, Vinyl Institute, of what they proposed to sample, and then our review and approval. And so one of the objectives was to get to identifying, what were the key similar exposure groups to identify. So I think it was kind of a collaborative process where they would propose, we would review and have comments, and then through that we got to the place where we had agreement on the sampling of protocol that for this OES, for this facility, these were the similar exposure groups that would be monitored. And then when we got that data, then we knew, from what was in the proposal that it was during manufacture of 1,1-DCA. So we really want to get to that ability to identify the similar exposure groups within an OES and then assess exposure for the similar exposure groups. So the advantage of a test order is that the data has not yet been collected. So you can have that back and forth and get to a sampling protocol that really accomplishes the objectives. When we're dealing with secondary data where, the data has already been collected, it's in the past, it can be difficult to separate out similar exposure groups, from secondary. Sometimes you might have the benefit of very detailed NIOSH health hazard evaluation where they'll present similar exposure groups and the data that responds to each similar exposure group. But that's more the exception in secondary data. So we're less capable of differentiating data we collect from secondary sources into similar exposure groups. When we do modeling, a lot of times we've used near field, far field modeling approaches. So, for example, vapor degreasing, where we'll identify the source of emission as the vapor degreaser, and then the model, basically it's a two-zone model, so it estimates exposure concentrations in the near field and then the far field. And so our practice has been, when we've used near field, far field modeling, to associate the near field exposures with what we call the workers, and the far field with the ONUs. Hopefully that gets at some of the considerations. I know this will be one of the charge questions, and we welcome additional discussion and comments and questions on this aspect.
So just to follow up, this was all done by EPA, essentially collecting information, not by anybody from EPA going out and actually looking at the operations and trying to determine it that way.
The test order process was the closest we got to that, where we're actually working with the actual industry representatives from these facilities in developing the protocol to do the sampling.
Yeah. Thank you.
Mm-hmm.
So, and just as a follow on, this is George, and I'm sorry, Heather, for jumping in. That test order was that just for inhalation, or was that also for dermal and all of the use scenarios?
Yeah, it was for inhalation, and the proposal from the Vinyl Institute for 1,1-DCA was to monitor at a facility that manufactures 1,1-DCA, as well as several 1,2-DCA manufacturing facilities where 1,1-DCA is produced as a byproduct. So we did get that data, but then, as I mentioned, a scope decision is that that'll be in the 1,2-DCA risk evaluation. For 1,1-DCA, there really weren't that many OESs. You really had manufacturer and the primary OES of reaction as processing as a reactive intermediate. There was the commercial use of laboratory chemicals that was identified. So those are really the main OESs, in addition to kind of the standard ones of distribution and commerce and waste disposal.
But I guess the point is the test order was for inhalation, not for dermal exposure, and not for looking at all of those.
Yes, correct. And so there was a desire to get dermal monitoring data, but I know there were issues associated with having a good test method to do the monitoring for volatile chemicals. So
it's all good. I was simply trying to clarify the dialogue around Mr. Wright's question.
Mm-hmm.
So thank you for that very thorough answer. And now, Heather, if you go, Dr. Lynn.
Thanks. Hi, Dr. Masick. Nice to see you. Thanks for the great presentation, walking through everything. I have a question that maybe I missed something, and now that you guys were talking more, I was like, I got to go back and reread the OESs and the difference between the 1,2-DCA and the 1,1-DCA data from the Vinyl Institute study. But I was kind of curious if you could clarify, and maybe I'm missing something, but I think you had like the facility that processes it as an intermediate that was used for, I think, a lot of the exposure calculations. And then I think that was mapped over as well to some of the processing as a reactant or processing as an impurity COU OES combinations as well. But I was kind of curious how you made the decision of what COU to put them in. This is kind of off of Mike's question earlier, because it looked like there were 4 facilities that they had data from, and one of them was the intermediate and 3 of them were producing it as an impurity or a byproduct. And I think 2 of those got mapped to manufacturing, and one of them got the Olin, Texas facility got mapped to processing. And unless I'm getting that mixed up. So I just wanted to clarify if I'm missing something, or is there a reason why sometimes impurity is mapped to processing and sometimes to manufacturing?
Yeah, we didn't use the impurity data in the risk evaluation for 1,1 DCA. That data will be used in 1,2 DCA. So to assess the OES where 1,1 DCA is used as an intermediate, we applied the manufacturer data from the test order.
Okay, thanks.
So, Dr. Kalushny?
Yes, hi again. Thank you for the presentation. It's still not clear to me why, carry on from the previous question, why dilutions were excluded. I believe in your presentation, I saw just an opposite, like in the slide 128 shows that it like waste handling happens a lot in the different scenarios. And as I understand, it's not neat material then. So it's one question maybe, and then I have another one. I don't know how is best to approach.
I mean, those are good questions. I think our approach was to use the most conservative weight fraction and then corresponding fraction absorbed for each OAS. But those are good comments, and I think I'll defer to the charge question. That's going to be one of the specific charge questions of, applying the fractional absorb. So consideration of where we could have used as the dilute, maybe to provide a more complete picture. We certainly welcome that kind of those comments and input.
Right, because in this situation, it's not exactly the safe way to go. But another question is
the fraction, the neat would be the highest, would result in the highest exposure, isn't that right?
But not necessarily the highest absorption.
But yeah, I think we'll defer to the chart, but we definitely would look forward to that kind of discussion and feedback there.
Yeah, thank you for explanation of a dermal absorption formula. It was very nice done, but I still don't understand certain players in the formula as it is called. It's basically a model for evaluation of volatile materials. At the same time, it's using the data from the wipe test. And those materials were not volatile or oily, right? So it's one thing. So where is kind of how correction for volatility happens? And also it's like a circular argument. It's uses 0.3% absorption obtained in the previous study, which isn't a question. And those factors kind of are still up in the air.
we definitely wanted feedback from the committee, and, you know, we have that specific charge question.
Okay, thank you.
So I see that, Mike, is your hand still up?
Yes, it is.
All right, please go, please go.
Okay. This is another one for which I have to kind of apologize. I've been looking at sort of two different reports involving sampling, and I want to make sure I don't have them mixed up. But did you or did the contractor or the Vinyl Institute exclude some data because it was collected under emergency or non-routine circumstances?
No, not that I'm aware of. I think we got the data, and they may have provided some additional characterization for some of the higher values they got.
But they didn't actually exclude it.
Not to my
Good.
knowledge.
Okay. Okay. I am thinking about the other sampling run. I apologize.
Yeah.
Okay. Dr. Schammel? Dr. Sammel.
Thank you very much. And thank you very much for that presentation. It was very helpful and answered a few of my questions as well. So I appreciate it. Just one sort of remaining clarification, just to make sure that I understand, relates to my previous question again as well. But with respect to the values for the actual loading that were used in the dermal loading or in the DEVL equation, we've got high-end values of 2.1 milligrams per centimeter squared and 1.4 milligrams per centimeter squared for the high end and central tendency. Was there any consideration or analysis of those levels of loading compared to what was done in the in vitro study? For example, when we say 0.3% of the amount that was loaded on the skin was absorbed, is there any comparison that you all considered for the relative amounts that might have been absorbed versus what was loaded on the skin for that particular model?
I have to say no, but I think that's a very interesting topic and point. So glad to hear more discussion, you know, or comment on that point. But no, not in terms of arriving at the exposure estimates for dermal for the workers.
Okay, understood. Thank you so much for confirming and for clarifying.
All right. So are there other questions from the committee? I actually have a couple. It's George Cobb. I have a couple. And I think I want to circle back to one that was asked before about diluted samples or diluted DCA. It seems like some of the uses that you're talking about, actually, the chemical would be diluted. You're talking about using as degreaser and those kinds of things. Perhaps that would by definition be diluted. So I'm wondering which conditions of use were included versus excluded just generally. And I didn't have a chance to read all of that. So were there conditions of use where there would be DCA in more dilute form?
Yeah, I think I unintentionally confused the issue. So for 1,1-DCA, the conditions of use were, as I mentioned, you know, fairly simple. You had manufacturing, which would be, you know, producing a product at, you know, a neat form, and then use of that as an intermediate would also be a neat form. We had data from safety data sheets that indicated that 1,1-DCA as a laboratory chemical could be at 100%. So I think that it's possible in waste disposal. I could see that there's more dilute concentrations, but we generally, our approach is to use what we think could be the highest concentration. So even in waste disposal, we assume there could be situations where it's handled at 100%. But
Okay.
I could definitely see there's more to the picture for waste disposal. I shouldn't have used the vapor degreasing. I was trying to just illustrate how if we have, there may be times where we have a condition of use from the scoping document that we feel we need to subdivide because exposure potential can vary greatly. So I use it as an example, but it's actually not a condition of use for 1,1 DCA. But yes, definitely if there was a use where there was formulation and then end use, that would definitely have been a case where we would have had dilute, but it didn't really apply here, other than the waste disposal, which I think that's a good comment for us.
Okay, so great. Thank you for that clarification. Now, my next question can seem to be a little almost rambling and maybe even towards off topic, but it really does, in essence, get to the scientific validity of the approach. And my question is, when you've decided to take the 1,1 DCA as an impurity in 1,2 DCA and assess that in the 1,2 DCA evaluation. My question is several-fold. First of all, will that 1,1 DCA exposure be wrapped back into this assessment? Will it be wrapped into the 1,2 DCA overall toxicity assessment? How will that be handled? And I think we need to know that to know how to handle this overall assessment.
It's a good point. It is something that came up in the scoping. There was a lot of discussion about how we would handle 1,1 DCA produced as a byproduct from 1,2 DCA manufacture. Where would that assessment be? And so one route we could have taken was to assess that in the 1,1 DCA risk evaluation. But the decision was made that we wanted to assess the byproducts of 1,2 DCA in the 1,2 DCA risk evaluation. So that second kind of collection of monitoring data was monitoring at plants that manufacture 1,2 DCA, but workers were sampled for 1,1 DCA exposure, just to see what exposure levels would be from a plant that 1,1 DCA is produced as a byproduct. So there is a separation step done after manufacture, and so there is the presence of 1,1 DCA at these 1,2 DCA plants. So that was a scoping decision. It could have gone the other way, where we would have included it in 1,1 DCA, but I think the overall feeling was that it would better serve and covered in 1,2 DCA.
So I really appreciate that answer, and I was going to say that was not a shoot the messenger kind of question. It was really to try to get to a little clearer understanding. I saw Dr. Lowett appear and then disappear, but I almost prefaced my question with, I think this might be one that she wanted to answer, but I'm not sure if EPA feels that's an adequate answer. I do, but I'm not. I don't want to dismiss your colleagues if you have something else you'd like to add.
No, I just wanted the simple answer is that we're going to be handling 1,1 as a byproduct in the 1,2 assessment. And that decision has been made. There are multiple byproducts. We're going to do them all together.
So that would be a 1,2 DCA as all of the toxic byproducts potentially toxic byproducts together.
There are multiple ones where we're putting the byproducts together.
Yeah. And there's certainly different ways to slice and dice all of that. And I think I appreciate that, but I'm not in the trenches with you folks. So, but I think I appreciate that there's multiple ways to do that. Okay. Thank you for indulging my overall question that has probably 4 different assessments that EPA is doing at the same time, all wrapped up into that question. Okay. So I think we're towards the end of the EPA presentations. At this point, I'd like to circle back and see one from the committee. Are there any final questions for EPA before we move into the responses to the charge questions? And then I'll circle back to EPA real quick before we're done here too. I see Heather Lynch.
Sorry, I'm going to beat this dead horse a little bit more. My last confusion, George, thank you for asking that, Dr. Hobbs, because I had the same little confusion about the impurities, and thank you, Dr. Lowett, for confirming the byproducts are going into the 1,2 DCA assessment. But it's still, this is my confusion from earlier, circling back to it, that the Freeport Olin facility is listed as an example of processing as a reactant. And as far as I'm aware, that's one of the facilities that was sampled for producing 1,1 DCA as a byproduct from 1,2 DCA manufacturer. But they're in the processing COU as an example here. But yet that data wasn't used. The data from manufacturer as an intermediate was used. So I'm confused why that Freeport facility is still being included in this one if all the byproducts are going into 1,2 DCA.
So, Dr. Lynch, I think that's a good comment to be putting in the response to the charge question. A recommendation on how we did that or an alternative point of view.
Okay. All right. Thank you. I just want to make sure I wasn't missing something. Thank you.
Excellent. Okay, if there are no other questions from the committee, are there any clarifying statements or questions from EPA about what we've covered today?
Oh, so Anna Lowett again. We have had a few questions to our staff over the course of the day that we haven't fully answered. There were a couple systematic few questions earlier, and I think there were maybe a couple other lingering ones. We're going to work on writing written responses to those and have Dr. Burris read them into the record in the morning. So if you don't mind, we'll start out the morning with some responses to a couple of those questions we didn't fully answer.
You're on mute. You're on mute.
That will be excellent, and I appreciate your willingness to do that by in the morning. That's pretty aggressive work there. So I appreciate that. Okay, well, now it is time for public comments. So I'm not sure I have the list of public commenters. Let me see if I can locate that.
Dr. Cobb, it's in the chat, numbered as 1, 2, 3. So we have it organized already. And then we used to have Paul DeLeo, so he'll be number 4. But if you look under the participants, it's already numbered.
In the chat?
In the participants, I meant to say participants, not chat.
Oh, hold on. I see.
Yeah. Mm-hmm.
Mm-hmm. Okay. So thank you, Allie, for keeping me straight here. So our first commenter is Adriana Antezana, excuse me.
Yeah.
And so you have 5 minutes. And thank you for joining us.
Yeah, good afternoon, everyone, and thank you for the time to speak today. My name is Adriana Antizana, and I'm a staff scientist with Earth Justice. So today I wanted to remark on 2 points. First, in response to charge question 3, the SACC should support the use of 1,2-dichloroethane as an analog to assess 1,1-dichlorophane's toxicity. And second, in response to charge question 1, that the SACC should call on EPA to account for the releases of 1,1-dichloroethane from weather events and other unintended but reasonably foreseen chemical incidents. So to resolve significant 1,1-dichloroethane data gaps, the EPA appropriately identified 1,2-dichloroethane as an analog, as we heard earlier, and EPA's methodology demonstrated similar structural, physical, and chemical properties, similar toxicity, and comparable metabolic pathways, including the formation of chloraldehydes as metabolites. To challenge the metabolic similarities, the American Chemistry Council referred to a single master's thesis that found suggestive evidence of a difference in metabolism between 2 chloroacetylaldehydes in vitro systems. However, the study itself states that the significance of this finding in an intact cell and in vivo is not clear and warrants further research. And moreover, while the ACC alleges a different potency between 1,1 and 1,2-DCA, the OECD's guidance on grouping of chemicals notes that when applying a quantitative read-across, one technique for estimating missing data is to take the most conservative value of the closest analog. Therefore, we support utilizing 1,2-dichloroethane for read-across, and is consistent with that approach and utilizes the best available science to derive health protective points of departure. And turning to my next point, in the draft risk evaluation, EPA excluded the largest surface water release of 1,1-DCA because it resulted from a storm event in Lake Charles, Louisiana. However, TSCA mandates that EPA considers known, intended, and reasonably foreseen releases of a chemical. Releases from storms and other chemical incidents, while unintended, are both known and reasonably foreseen. As we were reminded with Hurricane Francine just last week, extreme storm events are a regular occurrence and are in fact worsening, especially in Louisiana and Texas, where both 1,1 and 1,2-DCA are primarily manufactured, used, and released. Storms cause facility power outages, unplanned shutdowns, and equipment failures. In NOAA's tracking of billion-dollar weather and climate disaster events, which covers only a small subset of these severe events, it shows that in Texas, for over 39 years, there's rarely a year with 7 or more events, while in the last 5 years, there hasn't been a year without at least 9 events. And in Louisiana, over 38 years, there were no more than 4 events in a single year. But over the last 6 years, there have been at least 6 severe weather events annually. In addition to excluding the evidence of known storm-related releases, EPA also failed to consider reasonably available data on other chemical incidents, including leaks, spills, and explosions. These incidents occurred on nearly a daily basis from 2022 to 2023 in the United States. Had EPA reviewed state data on chemical incidents, they would have found that just 2 years after that 2020 storm in Louisiana, the Louisiana Department of Environmental Quality reported over 4,500 pounds of 1,1-dichloroethane released from an equipment leak. And for context, only about 14,000 pounds of 1,1-DCA were released from TRI facilities in Louisiana in 2022, and only one facility in the entire U.S. even reported releasing over 1,500 pounds of 1,1-dichloroethane that year. Louisiana also reported incidents of 1,2-dichloroethane releases in 15 of the last 16 years. So in conclusion, the EPA needs to collect information on chemical releases from state and federal authorities like the Texas Commission on Environmental Quality and the Coast Guard's National Response Center that both have reported 1,1 and 1,2-DCA releases from events and storm weather-related releases. This data shows that unintended releases are reasonably foreseen and their frequency, severity, and expected releases can be reasonably accounted for. By ignoring extreme weather events and other chemical incidents, EPA is writing off thousands of pounds of releases that communities will inevitably be exposed to this year and on. That's all I have for today. Thank you for your time.
Thank you. Thank you for that presentation. And now we can go to our next presenter, which is Marissa Kreider.
And very quickly, before we go on, I just want to make sure that the timer, the 5-minute timer, is on the screen.
Thank you, Alan.
So please put the 5-minute timer on the screen so we all can see that, please.
Good afternoon. My name is Marissa Kreider, and I'm a board certified toxicologist with the Health Sciences Group at Stantec. We have been supporting the Vinyl Institute on issues related to the ongoing risk evaluations of both 1,1-dichloroethane and 1,2-dichloroethane. My comments today have been prepared on behalf of the Vinyl Institute, their members, and affiliated consortia. The VI has submitted substantial formal written comments with additional context to the docket, but at this time I seek to highlight the most important points of VI's review. First, EPA's decision to rely on 1,2-dichloroethane as an analog for 1,1-dichloroethane for all human health effects is neither transparently supported nor justified on the basis of existing hazard data for 1,1-dichloroethane. The tools upon which EPA relied to determine analogs for 1,1-dichloroethane produce many potential analogs. EPA's decision methodology for identifying and selecting an appropriate analog amongst the options was not clearly described. Where hazard data for 1,1-dichloroethane exists, there are clear inconsistencies with 1,2-dichloroethane, including for key effects such as metabolism, kidney toxicity, and cancer, among others. On this basis, 1,2-dichloroethane may not be a suitable analog for 1,1-dichloroethane for all endpoints. EPA should consider alternate approaches to identifying analogs for 1,1-dichloroethane, such as relying on a categorical approach or use of data for a more structurally similar germinal dihalide, such as dichloromethane. Because 1,2-dichloroethane is used as an analog for health effects of 1,1-dichloroethane, the 1,1-dichloroethane risk evaluation is predicated on the accuracy of the hazard assessment of 1,2-dichloroethane. VI has further concerns regarding the appropriateness of many of the conclusions associated with 1,2-dichloroethane hazard assessment and the use of key studies for the derivation of health benchmarks for 1,2-dichloroethane. In this hazard assessment, EPA identifies several key health endpoints upon which they base health benchmarks for use in risk evaluation, including, among others, immunotoxicity, reproductive toxicity, and cancer. In drawing these conclusions, EPA disregarded key findings on the weight of evidence of these hazards. For both immunotoxicity and reproductive toxicity, EPA relied on studies that produced effects that were inconsistent with the weight of evidence for those endpoints. Based on their exclusion of key studies they deemed uninformative on the basis of reduced water consumption in animals during dosing. However, such studies may provide important weight of evidence considerations regarding hazard potential for 1,2-dichloroethane, as well as important dose response information that could critically alter conclusions reached by EPA. On cancer, in addition to relying on studies for both oral and inhalation cancer dose response for which underlying concerns exist, EPA did not thoroughly evaluate mode of action or consider a potential nonlinear dose response for 1,2-dichloroethane. Evidence for in vivo mutagenicity and genotoxicity of 1,2-dichloroethane is equivocal at best, and a recent study focused on eluding mode of action for carcinogenicity of 1,2-dichloroethane concluded the mode of action is likely to be non-genotoxic. Therefore, a careful assessment of mode of action and its implications for the development of screening values is essential. Notably, the concerns about both the hazard and dose response assessment for 1,2-dichloroethane extend to concerns about the appropriateness of the proposed occupational exposure values for 1,1-dichloroethane noted in Appendix N of the risk evaluation. The proposed OEVs are orders of magnitude lower than currently enforceable occupational exposure limits for both 1,1-dichloroethane and 1,2-dichloroethane. The most conservative OEV is based on cancer, in spite of lack of evidence of cancer in working populations based on available epidemiology for 1,2-dichloroethane. Lastly, in response to the agency's test order for 1,1-dichloroethane and following an EPA-approved study plan, the VI conducted a study to collect worker and occupational non-user inhalation exposure data. While the EPA rated the VI study as high quality and incorporated a portion of the data set into their worker exposure and risk assessment for 1,1-dichloroethane, data collected from 3 of the 4 representative facilities were not considered for any of the occupational exposure scenarios evaluated by EPA in the risk evaluation. It's unclear why these data were excluded, particularly as their inclusion may impact risk conclusions made based on the central tendency values for the data set. Further, qualitative information on task frequency and duration provided in the test order response at EPA's request is not represented in the agency's current assumptions for the worker exposure estimate. With that, I thank the agency and the SACC for their time and commitment to a high-quality review of these assessments. I hope that these concerns and comments are considered and addressed to facilitate both an improved risk evaluation for 1,1-dichloroethane and hazard assessment for 1,2-dichloroethane.
Thank you. Our next public commenter is Paige Varner.
Yes, hi, good afternoon. My name is Paige Varner, Dr. Paige Varner, and I'm a scientist with Environmental Defense Fund. Thank you for the opportunity to comment. We have submitted the following comments and more in written comments to EPA and the SACC, but I wanted to touch on just a few points here. First, as it relates to the draft 1,1-dichloroethane risk assessment, EPA underestimated exposures and risks, particularly in vulnerable and highly exposed populations, and should more holistically assess these risks in the final risk evaluation. This underestimation is specifically evident in EPA's assessment of risk to potentially exposed or susceptible subpopulations, or PESS. Here, EPA improperly over-relies on a 10x uncertainty factor for human variability, also called the interspecies UF, to address risks to pests. For example, EPA relied on the 10x interspecies UF to address the increased susceptibility of 1,1-dichloroethane for those with chronic liver disease, Parkinson's disease, and other neurological disorders, and the aldehyde dehydrogenase 2 mutation. The use of the interspecies UF is contrary to its intended use, which is merely to account for variations in susceptibility within the general population of healthy adults, not susceptibility based on existing conditions. Other pests that EPA identified, such as smokers or those exposed to secondhand smoke, were not assessed or addressed at all in the draft risk evaluation, even though EPA identifies that smoking cigarettes is a source of between 51 and 110 micrograms of 1,1-dichloroethane per cigarette. EPA must therefore assess the aggregate risk of 1,1-dichloroethane exposure to smokers or those exposed to secondhand smoke, as this subpopulation has been identified as a pest because they are more highly exposed. Overall, EPA must assess risks to distinct groups of pests by separately analyzing exposure, dose response data, and/or modifying factors specific to each group based on their high exposure or particularly higher susceptibility, rather than rely on the 10x interspecies UF. As it relates to 1,2-dichloroethane hazard assessment, EPA should continue to use the points of departure selected in the assessment. Specifically, EPA should use the BMCL from the 2006 Dow chemical study for the inhalation non-cancer acute point of departure, which is based on benchmark dose modeling of nasal lesions in rats exposed to 1,2-dichloroethane. In charge question 6, EPA notes that its benchmark dose technical guidance states that extrapolation sufficiently below the observable range may be too uncertain to reliably estimate BMDs or BMDLs for the selected benchmark response, and that in such cases, BMD modeling is not recommended and obtaining more data or using the NOAEL/low AL approach may be warranted. However, this statement is qualified in the footnote of the guidance that a detailed decision process is not provided because datasets vary and therefore the decision to not rely on BMD modeling should be made case by case. In this case, BMD modeling for nasal lesions has strong goodness of fit metrics, and the BMD is actually above the study NOAEL, with the BMDL being within the same order of magnitude as the NOAEL, not sufficiently below. On this basis, it is scientifically sound to use the BMDL as a point of departure. Further, as described in the BMD guidance, the BMD approach incorporates more information than the NOAEL or the low AL process, and the NOAEL is really just a consequence of the fact that any finite study has an inherent limit of detection. Therefore, the NOAEL is actually of little practical utility in describing toxicological dose-response relationships and does not represent a biological threshold and cannot establish that lower exposure levels are necessarily without risk. Rather, BMD modeling incorporates underlying dose-response data, incorporates variability and uncertainty in its use, and should be used in selection of the inhalation non-cancer acute point of departure. We also urge EPA to continue to use the Gavage study in the 1982 Munson et al. Study for the oral non-cancer short-term and chronic points of departure, and to use the mouse study from the 1978 NTP study for quantitative derivation of the oral slope factor with qualitative support from the rat study from the same source. The justification for use of these studies for the POD and slope factor derivation are detailed more in our written comments. Lastly, as it relates to charge question 8, EPA should continue to use a 0.3% dermal absorption factor in the draft risk evaluation. The lower absorption factors considered in the charge questions are based on the overly simplistic assumption of vapor pressure only and does not take into account occupational scenarios such as down the glove exposures where different rates of evaporation will occur. Thus, to fully consider the range of potential exposures to workers, EPA should continue to use the 0.3% dermal absorption factor. Like I said, we've submitted these comments and more in our written comments to the EPA and SACC, and thank you all for your time.
Great. Thank you for the comment. And some of those actually reflect comments that the committee had made on previous assessments for other chemicals. So thank you. Our last public commenter is Paul DeLeo.
Thank you. Good day. I'm Paul DeLeo. I'm a Senior Director of Chemical Management at the American Chemistry Council, and I wanted to express my appreciation to EPA and the SACC for this opportunity to provide these oral comments on the draft risk evaluation for 1,1-dichloroethane and the draft human health hazard assessment for 1,2-dichloroethane. Please note that ACC provided written comments on these two documents that are available in the associated docket. Today, I'd like to summarize a few points as they relate to charge questions that will be discussed during these meetings. ACC has repeatedly commented to EPA and the SACC on foundational elements of the EPA risk evaluations, and we find that some of the same issues occur in the 1,1-DCA risk evaluation. Among the most basic issues is that of tiered risk assessment. Standard practice for tiered risk assessment starts with simple screening approaches and refining hazard and exposure analyses as needed. We found in some cases EPA goes to a refined and more sophisticated approach when it does not need to, or in other cases, risk determinations are made based on screening level analysis when refinement is warranted and appropriate. I'll provide a couple examples from the risk evaluation. With regard to charge question 2, EPA requested comment from the SACC on strengths and uncertainties related to the read-across approaches used for the selection of the analogs of 1,1-DCA for hazard data for aquatic organisms. But it's unclear why read-across as a potential refinement is needed in this case. The draft risk evaluation notes that there are high-quality acute and chronic studies available for fish and aquatic invertebrates. Moreover, 1,1-DCA is a pretty simple polar organic compound with non-specific aquatic toxicity that would be expected to be directly related to the octanol water partition coefficient. So while it may be of academic interest what analogs might be suitable for environmental hazard assessment of 1,1-DCA, and it's appropriate for the SACC to weigh on this question, EPA would be better served by receiving recommendations from the SACC regarding problem formulation and a decision framework for ecological risk assessment to avoid unnecessary work. On the other end of the spectrum is charge question 10C regarding EPA's application of the dermal exposure to volatile liquids model and occupational exposure assessment. As part of EPA's approach to dermal occupational exposure assessment, it uses this very simple model with unrealistic dermal loading and exposure assumptions that include complete coverage of the hand with a non-volatile oil. In this case, refinement would be appropriate and is within EPA's capabilities. In fact, in EPA's 2020 risk evaluation for carbon tetrachloride, it used the American Industrial Hygiene Association's IH skin perm model to estimate dermal exposure as the mass that is absorbed through the skin using the dermal loading, exposure duration, and physical chemical properties of the chemical, including losses due to evaporation. We encourage the SACC to provide EPA with guidance on more appropriate dermal loading factors for 1,1-DCA and more appropriate dermal exposure models to estimate occupational exposure to 1,1-DCA. Finally, I wanted to comment on charge question 3, which is focused on the human health hazard data for 1,2-dichloroethane as a surrogate for 1,1-dichloroethane. And of course, this is a subject, will be a subject of a lot of the conversation. We want to restate our concerns that we expressed in our written comments regarding the scientific defensibility of read across from 1,2-DCA to 1,1-DCA, given differences in potency and metabolism between the two compounds. For example, we point out in our comments a relevant peer-reviewed publication that was not captured in the draft risk evaluation. The citation is Sharp and Carter, 1993. Their study identifies differences in metabolism between 1,2-DCA to 1,1-DCA, indicating that the ALDH2 gene mutation would not have as large an effect for 1,1-DCA as it would for 1,2-DCA because there is reduced dehydrogenase activity on 1,1-DCA. Thus, EPA should reconsider the appropriateness of the ALDH mutation as an indicator of a susceptible subpopulation for 11-DCA. Thank you for your attention. We appreciate the work of the SACC in reviewing these draft risk evaluations and look forward to this week's discussion.
All right. Thank you for your comment. And unless I'm looking at things incorrectly, I think that is our last public commenter. Allie, am I correct that that's our last public commenter?
Yes, it is. That is our last public commenter.
Excellent. So at this point, we've got 20 minutes or 25 minutes before we were scheduled to be done for the day. Let me ask Ms. Jenkins if you think we can get through your part of this in 25 minutes or maybe 45 minutes or so.
Well, we could try. I don't know.
Do you think that'll be pushing it?
I mean, I think if we had 45 minutes, I could do. Some of the other discussants want to weigh in on charge question 1. We have quite a bit of information, but I mean,
you
probably could get it done.
Okay. I think I'd like to try to do that unless there's an objection from Allie. Are we okay to do that?
Let me check here.
Yeah.
Some of the information. Let's see. Okay, so we are 14 minutes from the scheduled adjournment.
Yeah.
We do have the option of starting with charge question number 1 tomorrow, if we want to.
All right,
Let's see, and let me check the quorum if we have quorum. 1.
By the time we figure it out, we will have taken enough time. Let's just do that tomorrow. Let's just, and Allison, that'll give you time to get some more things aligned with comments. I know that we've had somewhat of a short time and everybody's working on multiple questions. So tomorrow we will begin with some clarifications from EPA. And first thing in the morning, and then we will start with charge question 1. I see Wayne Landis is.
Yeah, George, what kind of questions are we going to be needing to address tomorrow as we go through the charge questions? Because we're still getting in written information for the charge questions. Is this like to see where we are with it before we do the readout, or do we need everything ready to go to read into the record? Where exactly? This is only my second time through this.
Tomorrow would be what needs to go into the record, but that the first pass through, don't forget, we'll talk about question 1 and we'll get as many of everybody's comments as we can. Each person's going to have their chance to speak. Ms. Jenkins will go first, then Dr. Engel, then Dr. Hernandez, then you, then Dr. Lee, and then I'll open it up to the whole committee. And then if even then everything's not captured, at the end of every day, I circle back. In the beginning of every day, I circle back and say, are there any comments that we didn't capture from yesterday or the day before?
Great. So we're going to go through. We'll understand as a committee where everyone is at really for the first full time.
Yes.
Okay, good.
Now, if you need to have a committee subgroup, if y'all need to have a meeting, a dialogue in the morning beforehand at the lunch break this evening, well, this evening may be a little bit tight, but tomorrow evening, if you need to have a dialogue group to talk about things and to make sure things get aligned, the staff can arrange that within the Zoom platform, or you can arrange it yourself with a Zoom call.
So for within committee meeting, do we need to have someone from the staff or you on that meeting as well?
It does not have to be that way. The only thing we ask is that we not have, I think it's 11 of the permanent SACC
Right.
members on the committee on that call at any one time.
I know that you have put in a couple of comments. If you want to be included on my stuff, let me know.
Okay, I will do that. One housekeeping issue, since we're kind of closing up for the day, is that tomorrow I have to teach a class to the younger scientists in the world just a few minutes after this is slated to start. So I'm going to pass the chair role to Mary Fox for the hour or so that I have to teach. And she's going to keep you folks on track probably far better than I would. And so from like 9:05 or so, 10:05 Eastern tomorrow on, I'm going to have to be teaching instead of doing this. And then I'll circle back about an hour and 15 minutes later. So when you see Mary's smiling face, it won't be me. All right, with that, I'm going to turn it over. Mary, do you have anything you want to say?
Big shoes to fill, George. I'll do my best.
You'll be fine. You'll be better than I am. Okay, so let's turn it over to Allie and see what we have to close out the day.
Well, I just want to thank everyone for their participation and for their involvement with all the presentations today and doing such a great job today. So thank you very much. And I will now